I just want to welcome you all first to this online meeting. Unfortunately, we're still not all together. I'm actually connecting from the IAU, which is another big astronomy meeting taking place at the moment. In fact, I'm currently at, well, I'm in my room right now because I left, but I spent my day at the booth, which represents SCAR, so that the people here at the IAU can see a big map of Antarctica with all the places where you guys are doing your projects. In fact, if any of you are at the IAU physically, please come and see me. It'd be good to see some familiar faces. And with that in mind, I will maybe start a little bit on the early side, and so this way we don't burn too much contingency at the beginning. I think we've reached critical mass. I see 31 participants. And so I'd like to give the first presentation for Rui Wang. Can you please unmute yourself? And I can ask all of the speakers to also turn on their cameras so we can also see you. I think it's a lot more, much nicer to see you guys in this black sea of names. Yeah, it's much nicer to see you. Thank you. So I'm going to shut up now and give you your 10 minutes. I will give you a 2-minute warning when it's time. Okay. And don't forget to unmute. Yes.
Yeah, can you see my slides? Can you hear me?
Perfect. Go ahead.
Okay. Hello, everyone. My name is Rui Wang from Polar Research Institute of China. Today, I would like to introduce our the lower and middle atmosphere ladder system at Zhongshan Station. As one of the most powerful active remote sensing technologies, LiDAR has been widely used in the observation and research of the Earth's atmosphere in recent decades. Many stations have used LiDAR to observe atmosphere in Antarctica, such as Davis, South Pole, Reservoir, McMurdo, and Shower. China joined the LiDAR team 2 years ago at Zhongshan Station.
Sorry, ma'am, we are not able to see your screen. Could you remove the window in front of your presentation, please?
Can you see it now?
Yeah, we had it earlier, but now it's disappeared. It's a black screen.
I don't know what's the, yeah.
I think it's when you maximize your window. I think before you press the button to maximize your window.
I'll stop share screen. Yeah, we can see it now.
How about now?
All good.
Oh, okay. Our LiDAR system is the Palace, which is a synthetic LiDAR system, which began to be established from the summer part of the 35th Chinese expedition at Zhongshan Station and continued its reconstruction during the next year. During the 35th Chinese expedition, we built a sodium Doppler LiDAR, and a year later, we built the lower and middle atmosphere LiDAR system, which include a Rayleigh scattering LiDAR, a pure rotation Raman LiDAR, and a coherent Doppler wind LiDAR. With this LiDAR, we can observe the boundary layer, the troposphere, stratosphere, mesosphere, and the thermosphere. This is the schematic of the wind LiDAR, which is based on a fiber laser. It can measure the wind.
Excuse me. Sorry, I think we still only see your non-presentation slides. So we're only on your first slide.
Oh, what's What's the matter? I'm sorry.
I think you have multiple screens showing differently, but we can see your non-presentation slide. So we are stuck on the first slide.
啊，要不你帮我放，我看见你帮，哎呀，我有微信也没看。
So I suggest getting out of presentation mode altogether. It may be the easiest trick here.
I don't know what's the matter.
There you go. Now we are on coherent Doppler wind LiDAR. That's the
Yeah.
title. Yes.
Okay. Can you see the
Oh yes.
slide?
Yes.
Okay,
Oh, yeah.
okay. Sorry. Yeah, at least the schematic of the Doppler wind ladder, which can manage the wind among the boundary layer. And this is the schematic of the Roman ladder. It established the 533 nano laser light and connect the signals with a 200 nanometer telescope and with a band pass filter, we filter the signals, and after it, we use the two splitters to separate and divide the signals into three parts. An elastic Mi channel and two Roman channels. The temperature is retrieved from the relative strength of the pure rotational Roman scattering of the nitrogen and oxygen based on Boltzmann distribution. The Rayleigh Mi scattering ladder module share the telescopter with the sodium ladder and share the laser with the Roman ladder. It employed the Rayleigh scattering of the air molecule to get the relative density and get the temperature from the relative density. Our later observatory located at the southeast of Zhongshan Station. They are settled in 9 shutters. These are the photos of our system. These are the photos during the daytime, during nighttime. And next, I would show some results. On the left are the result of the wind ladder, the wind and wind speed and the direction of the wind ladder, and on the right are
I believe we have lost our speaker. Can you guys hear me?
Yes, I have lost to the speaker.
Okay, so it's not me. It's always hard to tell if it's speaker or listener.
We are the only two left behind in the meeting.
Let's see if we can do something here. Yeah, connection looks good. Let's not up to a good start technologically. Rui, I don't know if you can hear us, but we cannot hear you. We have a frozen screen on your side, and we have no sound and no movement from the video. I'm afraid we have still the same problem. So I'm going to suggest that we move to the next presentation, and we'll make sure that we get back to really doing discussion time here. Let's see. If you can hear us, if you can stop your sharing, and we'll move to the next speaker, to Dr. Chen, who's going to talk about sodium layer coupling. So just a reminder for those who logged in with us a bit late, please put all your questions to the speakers in the Q&A at the bottom, so that the speaker can address them in written form for everybody to see. Yeah, I'm getting a message saying PRIC has started screen sharing, but I don't see anything. Are we having a continental issue with the internet here? Aha. I'm not hearing anything, and I'm not seeing a presentation yet. I sort of heard something briefly. I wonder if it's a regional problem.
I'm afraid it thinks that way, right? Very unstable internet connection.
Yes. Okay. Well, let's be creative here and try to shuffle the speaker list around here. Dr. Lee, the third speaker, are you able to hear us, and can we hear you?
Yes, I'm here.
All right. Can you try to share your screen, and we'll get back to our other two speakers at the end of that third of the session.
Yes, sure.
So sorry to put you on the spot like this. It's live television. Never works the way we think. Go ahead and share your screen, and when you're ready to start, and I will give you 2 minutes a warning when it's time to move on, and we'll get back to our previous speakers later. Go ahead, you can see your slide. Very good. Well done.
Okay. Hello, everyone. My name is Xiaoyan Li, and I'm glad to be here to introduce the progress and status of AST3 project. And my talk is on behalf of all the team members of AST3. Antarctic Survey Telescopes project was sponsored by Chinese Center of Antarctic Astronomy in 2010. It consists of 3 wide-field telescopes with 500 millimeters aperture, and the main scientific purpose include supernova, exoplanets, variables, etc. And Dome is the highest peak on the Antarctic plateau, and it has almost the best thing on the Earth. The medial thickness of the boundary layer is about 14 meters. And according to the recent research, the medial thin above the boundary layer is about 0.31 arcsecond. AST3 project is an international teamwork, and the telescopes are developed by our institute and IoT, and data and observation system is charged by NAOC, and the energy module and the instrument module are developed by UNSW. This photo shows all the devices at Dome A in 2016. You can see the telescopes and solar panels, the weather station, the energy module, and instrument module. And as for the telescope, AST3 has a modified SMIT optical system. The tube length is only half of the traditional SMIT system. And it also has a large field of view of about 8 square degrees. And this kind of design makes the telescope has an enclosed tube to protect it from ice and snow in the harsh environment. And on the front window, a kind of ITO film is electrified to evaporate the snow and frost on it to keep the optical paths clear. And about the performance of the telescope, the left figure shows the photometric accuracy of the second telescope. At 10 second exposure, it is about 1% for 12 magnitude. And the highlight of the outcomes include exoplanet searching by Nanjing University team and gravitational wave counterpart observation by Pupil Mountain Observatory, and variable star research by national astronomical observatories. And since 2011, 17 person time have been to DOME for AST3 project. And the first telescope, as we can see at the right one on this photo, was installed in January 2011 and has been removed in 2017. The second one, that is the left one, was installed at DOME in 2015. Since 2019, Chinese expedition team to DOME has been suspended. That means the second telescope has no maintenance since January 2019. So all the observations stopped in 2019. And let's move to the third telescope. As the Antarctic plateau is the best infrared observation set on the Earth, astronomers had a plan to equip an infrared camera on the third telescope. To realize it, a reflector is added, and then the camera is moved outside the tube. And this design is beneficial for the camera installation and maintenance. And if we replace this part of module, and the telescope can back to the optical observation. Now the status is the infrared camera is under developing, and the telescope has completed and is commissioning in China. In February 2021, the telescope was installed at Yuan University in southwest China. And then an attended commissioning started since March of last year. And we use a CMOS camera and G-band filter. The field of view is about 2 square degrees, and with 1 pixel has a ratio of 0.4 arcsecond. Since March last year, the telescope has got more than 40,000 images that have constructed a good statistic sample. The left figure shows the sky grid of the tablet coverage for time domain observation. The different the color shows different limit magnitudes. About 97% of the tablets has finished up to now. The observation also include follow-up of gamma ray burst. And the next slide shows the telescope performance. This figure shows that shows the accuracy of the telescope. It is about 1% for about 16 magnitude stars on moonlight night. And this figure shows the FWHM distribution with observation altitude. And it is centralized to 2.3 arcseconds. And this figure shows the magnitude variation with the altitudes in different moon factions. As for the infrared camera, it is developed by Australia. And as we can see from the specific table, the detector is very brilliant. And the good news is the camera is close to be completed, but a bad news came in last week that the export application to China was denied by the Australian government. So that left the third telescope has no infrared detector now. And our next plan, as for the second telescope, we are waiting for the next expedition to Dormay, and we will get the status of all the devices and maintain it as much as possible. As for the third one, it will keep commissioning in China and wait for a good chance to Dormay. And we hope there will be a turning point about the export of the infrared camera. And that's all. Thank you.
Thank you very much, Dr. Lee. Please make sure you put your questions about AST3 in the Q&A. I'm sure there will be plenty of people interested to know exactly what's going to be the next few steps indeed about the telescope. So thank you for giving us this next plan coming ahead. Now I want to go back to our previous speaker, Dr. Chen. Let's see if we can have you now. Can we hear you? Let's have a look. Can see your slide, but I can't hear you. No sound coming from you. I kind of heard something briefly. It looks like the audio isn't working still on your side. Can see your mouse moving, can see your slide, but no sound coming out. I think we have a problem of bandwidth potentially with your side of the world, I'm afraid. No, still nothing. No, I can see your slide, but I can't hear anything. Okay, I suggest we'll try again a bit later during the day, maybe. Maybe there is some actual audio and not just bandwidth issues on your side. Then what we'll do is we'll move on to the next speaker, Icon Wen, who's going to give us a different type of presentation, something of interest to us who are keen on instrumentation about the snow mechanics taking place on the big plateau. Icon, do you have your slides ready? I think we're having issue with PARC altogether, so it looks like we may have some issues with several speakers here. It's a bit unfortunate. Yeah, I get that PRIC's network bandwidth is low. Now, can you please stop sharing your slides? I think we'll move to the next speaker, and I don't see icon 1 in the chat either. Okay, do we have a G20? Completely early on the schedule, so maybe not. Can you please, PRIC, Dr. Liu, can you unshare your slide, because we can't hear you. We still have issues with your end of the line. I wish I could go to a commercial break right now. And I think I'm missing my next couple of speakers. Maybe we can go back to Rui Wang. We didn't get the last half of your presentation due to some technical problems. If you're still there, maybe your problems have been fixed, maybe? I think it seems to be a continental issue altogether. I apologize to our audience right now. It's a bit underwhelming what's going on. There is a question from Michael Ashley in the chat. So if you are from a IST3, please jump into the chat. At least we can keep ourselves entertained with the Q&A session while we are trying to get some of our speakers back online. So I'm calling on our current speakers, either Icon Wen, Jiayang Li, or Ryu Wang. If I can hear any of you, I'm happy to jump back to you. But right now I'm getting absolutely no sound coming from any of you. So I'm a bit worried about bandwidth on your side.
Hello, Tony.
Yes, I hear somebody.
This is Jin Jun from Polar Research Institute of China. Here we have Rui Wang and Xiang Kaixin, who has not been successfully make presentation. I'm not sure how is the internet. Let me try.
Yeah, at least I can hear you, so it's progress. So if you have
just a moment, it's okay.
Yes, I can hear you.
Okay, just a moment.
Wonderful.
Let's go.
Wonderful.
This is Xiang Kaixin.
Go for it. I will give you a 2-minute warning, but I think we're doing fine now for time as we are losing speakers left and right. Go ahead.
Okay, Tony, I'm so sorry about that.
No problem.
But here I would give my presentation now. And my name is Xiang Chen from Polar Research Institute of China. The geospace in the polar region is always affected by solar activity. When the solar wind blows through the Earth, some part of particles, such as protons and electrons, will be captured by the Earth's magnetic field lines through reconnection at magnetopoles and magnetotail. This process normally triggers the ionosphere plasma flow with two convection cells in the polar regions, such as this stretch line plot. And meanwhile, the ionosphere thermosphere at 19 to 400 kilometers will also be affected by the solar UV radiation and the atmosphere disturbance from below. So the drag of the neutral wind, the ionosphere and thermosphere with a complex coupling process and wonderful phenomenon can be expected. Briefly, from Zhongshan Station in Antarctica, its geographic location is very good to do the geospace study. And for 2 times crossing aurora oval at dawn and dusk side. Zhongshan Station at night side is normally at polar cap region during the geomagnetic quiet time. And to investigate the space environment, several instruments have been worked at Zhongshan Station, and this includes high-frequency radar, belong to the super long radar network, and the traditional ionospheric digisound, and the all-sky image, which can capture the green and red aurora, and also the imagerometer and the magnetometer. And for the GPS TEC receiver, we can calculate the ionospheric total electron content. And in February 2019, a LiDAR system has been deployed. And this LiDAR system with 3 telescopes towards the zenith and a certain degree of zenith to the south and the west. It can measure the temperature, neutral wind, and CO2 lumber density at altitudes from 18 to about 110 kilometers. As one of the main features, the LiDAR could reveal the oscillational metal atom concentration phenomena. The density of SS layer rapidly grows within a narrow webs. It can span a few tenths of minutes to several hours. 4 factors are expected to cause this concentration, but the ionospheric sporadic ES layer is expected to be the most likely cause. And for the ES layer observed by ionosound, here we give an example for the strong ES, which could shield the F region equals. And another example shows the causal relationship between the ES layer and the SS layer by our rocket campaign. And on 14th November 2019, a strong ES layer above the metal main layer was detected. And this ES layer with detected sublayers could be easily identified. It was higher than the background density and more than 10 times. And before and after this strong SS layers, some other layers with a shorter time and duration can be also identified. And by comparing these 2 layers from LiDAR and ionosound radars, and we found the strong SS layer correspond to the strong ES layer, and many under the required geomagnetic conditions. As shown in the top panel, there are 3 peaks that's with high CO2 density, and the first 2 peaks were aligned to the enhanced ES layer, but its onset time is delayed about 10 minutes compared to the ES layer. And this is reasonable for CO2 ions transferred to atoms in the ES layer by neutralization. And moreover, by estimating the electron density, we found the ES layer is sufficient to provide the source of metal ions for SS layer. And furthermore, the ES layer with wave-like structures showed a good correlation with the SS layers when it descended to the lower heights. And with the DMSB satellite crossing, we saw the superdown radar flow reversal was connected to the aurora over boundary and the polar cap aurora arc. And the INO sound showed the ES with a descending trend, implying that superdown radar echoes from far to near range. And the periodic perturbation illustrated the role of the gravity waves. By using the superdown radar beam elevation angle to derive the height of the scattering volume, we confirmed the ES monitored by superdown radar precedes the DPS by about 1 hour. And this could be related to the ES with an elongation of about 500 kilometers along with the convection circulation. As the electron field contributes to the descending velocity by about 1/3, the gravity wave is thus important for the vertical motion of the ES layer. In a summary, the LiDAR has been operated for 3 years, and with 167 running days, we have found 44 days with observers SS layers event. And more than 3/4 are accompanied by the ES layer. This would make us study the ionosphere and thermosphere coupling process at Zhongshan Station in more detail in the future. And if any of you are interested, we are also glad to cooperate with you. And for this presentation, if you want to know more information, please read the paper. And if anyone for further questions, please email me or just leave a message at the screen. Okay, thank you for your attention.
Thank you very much for being such a perfect timer. Yes, indeed, please ask your questions in the Q&A. In fact, I think there is an open question right now for our first speaker. So make sure you pay attention to the Q&A if you're giving a talk. Fantastic, thank you. Let's see now, do we have now Icon Wen back online? Don't see Icon by name on the chat list. In that case, Jintuo, are you here? So your name earlier. So if you are here and if you are ready to present, it could be that we still have a sound issue from PRIC. I see you, but you're muted so if you're trying to speak. So we have still some technical difficulties with PARC here. Yeah, if you're an attendee, you can unmute yourself and talk, just to remind yourself that you can now do that directly. The IT group has allowed this functionality now, because I think it's probably a bit easier to do that way if we have technical challenges. So I don't have Icon Wen, I don't have G2O. Do we have Kijio Tian? Excuse me if I...
Yes.
Oh, there we are. So finally, somebody with sound working. Excellent.
Okay.
Are you ready to give your presentation even a bit early?
Yeah, sure.
Go ahead and share your screen.
Okay, let me.
Okay, we've got your yes, and we have yes, perfect. Go ahead. It's all yours.
So I'm Chegang Zhong. That's from Polar Research Institute of China, also Peking University. So I'm try to make a brief introduction what we have done or what we plan to do for the future for the Antarctic stations. That's my outline of my talk. Brief introduction and the Chinese stations and some conjugate observation result from together with North Hemisphere, but in Arctic region, and also some kind of astroscience and the future plans. So according to the priority for Antarctic science, we are basically covered a little bit for point 1 and the major on point 5, observe space and the universe. So up to now, China has established a comprehensive observation system for Zhongshan Station and the Great Wall Station, and also Arctic yellow level station, including magnetometer, auroral image, and spectrometer. So basically, most of our people that's working on how space weather activity on the polar region and global magnetosphere, ionosphere, and coupling, and even neutral atmosphere. So in terms of Antarctic station, we have now we have 2 major stations. That's the Zhongshan Station here, and also Great Wall Station, and also that is 2 summer stations. We are planning to construct another station that's basically in the polar cap region. So that's the North Bay region that's still in the plan. Okay, for Zhongshan Station, we have equipment with many aurora equipments like all sky cameras, multi-channel spectrometer, and that's monochromator all sky image, and also aurora spectrograph and small scale aurora imager and multi wavelength all sky images. That's all kind of equipment related to aurora. So, and the nice things we actually could get the global picture and as well as a fine picture of aurora. That's a nice thing to do. And beside aurora equipment, we do have imageometer and ionospheric digital sound, and also high frequency scatter radar that's join the super band system, and also the other equipment to the major ionospheric stuff. So that's all. That's a kind of example. We joined the superline system and also can get a nice convection pattern. That's when the energy transforms from the solar wind to magnetosphere and even to ionosphere. And recent years we have set up a first sodium Doppler radar in Antarctica. That's nice things. Such kind of radar system could operate at day and night. I believe that is the first equipment can do such kind of job. That the covers from almost from the lower atmosphere to very high atmosphere. That's as an example, actually can capture some material and also the sodium layer. So that is a continuous observation for 56 hours continuously. That's from 82 kilometers and to 100 kilometers, 102 kilometers. That is, we can get the wind speed and temperature and density profiles. So that's even very fine structure for southern layers. And you can see that to show the system has very fine temporal and the spatial resolution. So beside Zhongshan Station, we also have a very comprehensive station in Antarctica. That's yellow level station. That's they conjugate each other. So that's it is very nice for those two major stations with equipment with comprehensive aurora observations. By using those equipment, actually we are able to identify that's complicated that's aurora images, and also decoding what's going on in the space, what's going on in the magnetosphere. That's the yellow level station, and also that's basically the same similar equipments like Zhongshan Station. That's a 3 wavelengths or sky aurora image and aurora spectrum graph, and the image aurora and all sky FPIs, and also magnetometer and inductive magnetometer and so on. So that's kind of what we got from, and that's a nearby station. That's a Chinese Iceland Aurora Observatory. That's operated since October 2013. That's aurora evolution with time, and that's so-called kilogram, and you can see the development of auroras. So by using those equipment, we are able to identify morphology of the bare side auroras. That's all kind of aurora, that's aurora arc, and deliberately aurora, and the radial aurora, and the hot spot aurora. Such kind of auroras also has kind of unstructured and structured aurora. That's just very fine pictures taken from the aurora equipment. And recently, the one of interesting stuff is the so-called short aurora. We have published quite a lot of paper in terms of the short aurora that's basically observed in the foot point of Casper region. So that's in terms of astral science. That's basically Arctica and Antarctica is very good window to the space for satellite traffic management. So that's the thing is look at so many satellites and also space debris in the space. That's all come together, meet together in the polar region. That's the only 3.6 the large object are tracked. So, and even tiny, that's the tiny debris can be fatal. So that's we are going to set up a telescope to monitor space debris. And that's a short movie from a yellow level station. As you can see, beside the aurora, you can see the spacecraft and even debris come and goes. That's very frequent. So that's for the plan. We are going to set up a space debris observation train from the Zhongshan Station and the Dome A, and also and the Tyson, the Convenors Station and Tyson Station, and together could be in the future together with some telescope in the Arctic region to set up a comprehensive train to monitor space debris.
1 minute.
So, the time is up.
1 minute.
Okay, so so that's a kind of a thing. So that's in Zhongshan Station we already set up the 3 kind of a telescope here. That's already set up for initial setups. And for the future, we are going to put some kind of instrument on the Chinese meteorology satellites for Fengyin 3 and 4. And we already got quite nice data sets for the future study. And in the coming years, that the Chinese ESA program called SMILE satellite will also cover take an image from magnetopause. That's kind of combine ground-based observation and satellite observation together. As one example, that is a satellite observation, that's a ground-based observation. We can see very fine structure that's aurora actually modulated by UF waves, and to understand further, to combine that's aurora observation and the spacecraft in the space. So that's basically my talk. Thanks.
Thank you very much. Question in the Q&A, and we're going to try to stay on the topic of space debris. Let's see if our next speaker can be heard. TOG, can you hear? Can we hear you? Let's have a look.
Yeah, I'm here, Tony.
Perfect.
Yeah.
We can hear you this time. It looks like PRIC's connection problems are getting better. That's really good.
Yeah.
So go ahead and share your slide.
Okay. I'll share my slide later.
Yeah.
I'm Professor Tu. Yeah, okay. Hi guys, can you see my slide?
Yes, we can see your slide. Go ahead and yeah, make it maybe on a bigger. Yeah, press play so we can see if we can see your bigger screen. Right now we can see your all the slides right now, not the main one.
Okay, yeah, this is the main one, the main page.
No,
okay.
we just see well, yeah, there we go. Now we see the proper slide. There you go. Go ahead.
Okay.
I'll give you a 2-minute warning. The floor is yours.
Okay, thank you, Tony. Hi guys, I'm going to go further into the detail about the debris observation about Professor Zhong has mentioned before. So my name is Tuo Ji from Polar Research Institute of China. So I'm the guy on the photo next to our telescope installed at the Zhongshan Station. And I want to thank SCAR and the meeting organizer for offering me this opportunity to present our work on behalf of our joint team. Our main collaborators are Travouillon and Peng Jiang, also from our PRIC team, and also Zhenliang Li's team from NIOT, and Hao Wenchen and Hai Jiang from NIOC. So I and Chen Wei attended the China's 38th Antarctica research expedition. I got back this April, where Chen Wei is still wintering over at the Zhongshan Station. So I spent 2 months at the Zhongshan Station this Austral summer, deployed and commissioned this small telescope array in this slide for space debris observation during my stay. So I'll give a brief introduction about the experiment at the Zhongshan Station. So before a virtual trip to Antarctic, let us first see a short video on the sky to at China's Yellow River Station in Arctic. It gives us some sense on how busy is the space traffic over polar region. So Yellow River Station looks at a latitude around 79 degrees north. So a little higher than Zhongshan Station and almost as high as China's Kunlun Station at Dome A. Kunlun Station is well known for its outstanding astronomical observations. As we will see here, Zhongshan Station is also a promising site for monitoring low Earth orbit targets. So investigating Antarctica as a window to the sky for satellite traffic management has been identified as one of the main Antarctic astronomy topics by SCAR. From 2018, astronomers in Polar Research Institute of China, National Astronomical Observatory of China, and the Nanjing Institute of Astronomical Optics and Technology worked together to study observing space debris in Antarctic. And finally, we deliver a small telescope array at the Zhongshan Station this summer. The telescope array includes 4 optical channels, each with a 15 centimeter aperture and a focal ratio of 2.8. Each channel is equipped with RGB filters with an FOV of 4.9 times 3.2 degree. So we use a commercial DWO CMOS camera with an average quantum efficiency of greater than 80%. The camera is with about 10,000 times 6,000 pixels. The plate scale is 1.85 arcsecond per second. We use an equatorial mount with a standard slewing speed of 12 degrees per second. The maximum speed could reach 60 degrees per second for really fast moving targets. So as the figure in the lower right shows, the tracing precision RMS is little than 2 arcseconds. So this video shows Xuelong, the Snow Dragon RV, parks at about 55 kilometers from Zhongshan Station during the heavy sea ice. And we started to unload the cargo onto the ice and use KA-32 helicopter to deliver the cargo to Zhongshan Station. All the penguins around. Okay, so this video on the left shows the hook got the astronomy instrument container out of the huge cabin of the Snow Dragon RV. In the video on the right, the helicopter is shipping the astronomy container to Zhongshan Station. Okay. So anyway, with the help of many colleagues at Zhongshan Station, we managed to deploy the telescope on the so-called Xianyu Peak. In English, the Fairy Peak. So the coordinates are on the slide. The yellow building is the LiDAR facility instrument for atmosphere physics study, while our telescope is on the right. The dome has not been installed at the time of the photo. So this is well, when we finished the install, there was still no night at the Zhongshan Station yet. This video was shot during our first order calibration of the telescope pointing by using solar and moon positions during the day. So at the time, the dome was not installed yet. So our sea view office with the iceberg around is really beautiful. And we can see the Russian progress station is 1 mile to the east. We can see their yellow oil tanks in this video. Okay. So finally, the winter is coming. When the night arrived at the Antarctic, we used bright stars to calibrate the polar axis pointing and build a pointing model with the aid of Point XP software. This video shows when Chenwei is doing the calibration on site. Finally, we achieve a polar axis pointing accuracy of 30 arcseconds. And we track bright stars and perform continuous short exposure to test the drift of the stars. By measuring the shift of the star centroid, the median drift is little than 1.5 arcseconds within half an hour. So this is our first light image of small Magellanic Cloud with a spatial scale of about 5 times 3 degrees. This is demonstrating the large field of view of the telescope array. So the image is synthesized from separate RGB exposure of 300 seconds each. The star image is fairly round with 80% of its energy within a 2.5 arc-second circle. So for the fast moving targets, we use two observation mode. The image on the left is in tracking mode. The fast moving target is the bright source in the middle, and the images of the stars are stretched out. The image on the right shows an image of the survey mode. The trajectory of the fast moving target appears as a short line segment, and the stars are point source. And this video shows our test of tracking mode using fast moving targets. So Chen-Wei is wintering over at the Zhongshan station right now, performing observations on space debris as well as exoplanets and bright quasars on daily basis. So but of course not in this harshing environment, but in our warm control room with nice food. So we hope our instrument will survive this winter as well as Chen-Wei with good logistic support at Zhongshan. In the long term, we seek to build an observational network for space debris observation and other astronomical science, all the way from Zhongshan, Taishan station, and to Kunlun station finally. And as a preview, we are planning for the 39th China research expedition now. We plan to perform a terahertz experiment at the Kunlun station with all the parameters listed for the instrument. Thank you all. Thank you.
Thank you very much. It's always good to have penguins and videos in your presentations. It's definitely great to see some live activity on the ice. Thank you very much. Q&A questions for Tuyo in the bottom of the screen. You know what to do. Thank you very much. You can unshare your presentation. And
okay, thank you.
Let's see if Tian is now back, and can we hear Tian?
Hello.
Yes, yeah, it's good. It sounds like things are getting better at PRIC, and we can hear you very fine. So please go ahead and share your presentations, and we'll jump right to you. I think we have, yes, the daytime seeing presentation. Off you go. All yours. I will give you a 2-minute warning.
Can you see the screen?
Yes, we have your full screen. Go ahead.
Okay. Hello, everyone. My name is Tian Qiguo from Polar Research Institute of China. The title of the talk is High Quality Daytime Seeing Windows at the Antarctic Taishan Station and Atmospheric Turbulence Measurements at Dome A. There are 3 parts in this talk. First, the optical turbulence intensity observations at Dome A using microthermal sensor will be presented. The optical turbulence intensity is denoted as CN2. Second, the measurement results of CN and CN2 at Antarctic Taishan Station will be discussed. The future plans will be given at last. Dome A is the highest point on the Antarctic plateau with altitude more than 4,000 kilometers. Taishan Station is nearly in the center between Zhongshan Station and Dome A with altitude 21 meters. One of the most interesting characteristics at Dome A is the very thin boundary layer. The median value reported by Bonner et al. Obtained using sonic radar is only 13.9 meters. Recently, Ma Bin et al. Reported that the boundary layer was below 8 meters for 31% of the time, with a median seen of 0.31 arcseconds, consistent with free atmosphere seeing. Seeing is one of the most important conditions for optical and near-infrared and astronomical observations. It is generally considered as a superposition of the atmospheric turbulence from 2 layers: the boundary layer near the surface and the free atmosphere above it. Meanwhile, the CO2 observations near the surface can provide key information for the choice of telescopes installation height. However, the direct measurement of optical turbulence at Dome A has not been reported up to now. This is a photograph and a schematic diagram of our turbulence measurement system. The temperatures and wind speeds can be measured at 0.5 meters and 2 meters using the corresponding sensors. The key information provided by this system is CN2, which was measured by microthermal sensor. The single level CN2 at Dome A was measured for 2 times. It was measured for the first time during 2015 January at 2 meters height, and 56 hours data was obtained. The results was shown as black histogram in the left figure. The blue line is the CN2 results at 31 meters at Dome C reported by Aristide et al., which show 2 peaks corresponding to the case of boundary layer above and below 31 meters respectively. The CN2 were measured again during 2019 January, and 132 hours data was obtained as a magenta line showing in the same figure. The total data was plotted in median CN2 at Dome A is between those at 24 meters and 31 meters at Dome C. We fitted the histogram with 3 cosines and found that the boundary layer in 14% of the time might be below 2 meters. It is helpful to simulate the scene behavior using the CN2 data. The scene contributions from the boundary layer can be calculated by integrating CN2 along the height as shown in this equation. Assuming that the optical turbulence intensity inside the boundary layer is uniform and adopting the boundary layer height in February reported by Bond et al. The boundary layer scene was estimated as shown in this figure. The median and mean boundary layer scene estimated using the median boundary layer height were 0.13 and 0.24 seconds, indicating that the scene contributed by boundary layer is remarkably small during our observations time. In 2019 January, we also observed the CN2 at 5 different heights with the help of the tower. We obtained 170 hours of data. For the sake of clarity, we plotted CN2 daily variation for the 1.5 and 3 meters height in the bottom figure. The median CN2 at 3 meters are about 4 times smaller than that at 1.5 meters height. It can be seen that CN2 at even 3 meters height can be smaller than that at 1.5 meter height by 2 orders. This is a direct evidence that the boundary layer can be lower than 3 meters, indicating that even installed the telescope on the snow surface can use the high quality seeing conditions during some time. We carried out CN2 observations at a tension station using microthermal sensor placed at a height of 2 meters and collected about 1,000 hours of data between 2013 December and 2014 February. The CN2 daily variation exhibits 2 minimum in the morning and afternoon every day. The median CN2 was between those observed at 17 meters and 24 meters at Dome C, and nearly twice that at Dome A. Thus, such weak optical turbulence indicate that the ground level scene of the tension station is also good, especially in the time windows of CN2 minima. To answer this question, the scene at the tension station was measured simultaneously using differential imaging motion monitor, which is short for DIM. This picture is of DIM, which was taken at the Antarctic tension station. The diameter of the telescope aperture is 365 millimeters. The equipment was mounted on the snow surface, and the height of the entrance pupil is about 2.5 meters. The scene observations using a DIM were carried out in the visible without filters on 2014 January 13 and 15 by observing the canopers. The cumulative exposure time of each measurement was 1 minute, during which nearly 500 images were taken for one scene For one seeing calculation, the team obtained 925 measurements of good quality in total. This figure shows the time series of seeing for these 2 days. It is clear that the seeing has a tendency to have a local minimum about 0.5 arcsecond around 18 o'clock local time. There was strong temperature agreement between the seeing minimum and that of the simultaneously observed seeing 2 as shown in the bottom panel. We estimated the seeing using the seeing 2 data as a black line shown in this figure, and the corresponding 1 sigma standard deviation is shown in the gray shaded regions. The estimated seeing also shows 2 clear troughs, and the profile is consistent with the observed data. We calculate the temperature gradients in 4 time intervals corresponding to the 2 CN2 peaks and 2 CN2 troughs as shown in this figure. The temperature gradient profiles of the 2 CN2 troughs are almost identical, with the temperature gradients normally disappearing, which also suggests that the 2 time windows might have similar seeing conditions. In a word, the high quality seeing windows might be opened at Taishan Station. It is planned that the multi-level seeing-2 measurements will be carried out at Dome A and Taishan Station to obtain the optical turbulence height profiles. The winter time seeing at Taishan Station will also be observed in the future. That's all. Thanks for your attention.
Thank you very much, Tian. We are right on time. In fact, we are slightly early because I think we are technically 1 speaker short. Thank you very much. You can unshare. And again, I invite the audience to ask you questions directly in the Q&A. Let's get ready for our next speaker. Let's see, we have Fujiadu online. Don't see Fujia online. In that case, we could try to get directly to Kyoka. Kyoka, I've seen you online, so you are here. Can you unmute if you are with us?
Can you hear me?
Yes.
Okay, I can start.
Definitely. Tian, can you unshare your screen, please?
Okay, wait a minute. Okay. Give me a moment.
No problem. I will tell you when I can see your presentation right now. Yes, I can see your presentation. Yes, we can see the slides, and we are on slide number 1. Wonderful. I will give you a 2-minute warning if needed. Otherwise, you go ahead and take it.
Okay. Thank you. I'm Kyoka Murase, a graduate student from Sokendai, Japan. And today I would like to talk about the impact of the mesospheric ionization due to energetic electron precipitation, so-called EEP, during substorm growth phase. This talk is based on the paper Murase 2022. Oops, sorry. Okay, first, let me introduce impacts of energetic electron precipitation. One of the important aspects of EEP is the energy deposition to the middle atmosphere. As shown in the right panel, electron with energies of 10 to 100 keV reaches the mesosphere, and they cause the ionization and chemical reactions at the mesosphere. And it is well known that this affects the neutral atmospheric compositions, such as odd nitrogen and odd hydrogen, which destroy ozone in the middle atmosphere. And one of the major sources of EEP is substorm, which are magnetospheric disturbances associated with auroral breakup. In recent years, the mechanism of EEPs has been studied for each phases of substorm, but the evaluation of EEPs and resulting ionization is not sufficient. And especially in terms of precipitating flux and its spatial extent. And radar observations are essential to detect and evaluate the ionization. Mesospheric ionization events have been reported using incoherent scatters and MST lasers, such as Pfizer and Panji laser. Recently, the ionization during recovery phase with pulsating auroras have got attention as a major source of the ionization. But the EEP during growth phase was not considered as important source of EEP. The EEP mechanism during growth phase is known to come from the magnetospheric structure during the growth phase, like this. Magnetic fields in the night side magnetosphere are thinned and stretched. These highly curved field lines violate the adiabatic invariant of particles, which result in pitch angle scattering and then precipitate into the atmosphere. This process is so-called field line curvature scattering here. And as you can see in the bottom, EEP region during growth phase is longitudinally extended. So the whole structure of the extent of the EEP was not captured by observations. So we can say that the total impact area of the growth phase EEP has been underestimated. So the purpose of our study is to evaluate the impact of the ionization during growth phase and compare the impact with other phases, especially focusing on the impact area. And here I describe the observational datasets and simulations we used. We used mesospheric echo power observed by the Panji radar at Showa Station as a proxy for the ionization due to EEP. In the event we report here, the data of EEP flux from satellite were also available, but today we're not going to show the results of the calculated ionization rate using the particle transport simulation. But global MHD simulation was also conducted to estimate the spatial extent of EEP events, assuming the scattering mechanism during the growth phase. And about this, I will give a detailed explanation later. And first, we show the overview of the ground-based observation at Showa Station. The event was on 24 to 25 July 2018 during a moderate substorm. In the left panels, altitude time variation of the echo power as observed by the Panji radar, and its temporal variation and the cosmic noise absorption at Showa Station. And the vertical black line here shows the timing of the substorm onset. And during the late growth phase here, the lowest echo at 68 kilometer altitude was detected by the Panji radar. And in the right panel, at the timing of the lowest echo, CNA and CNA contour and all sky aura images are shown here. And the CNA was aligned in east and west direction at the time. This longitudinally extended structure is consistent with the EEP during the growth phase. And EEP continued for 20 minutes during growth phase, and its intensity was comparable to after the substorm onset, as you can see from here. Here we show is a result of estimation of the spatial extent of EEP. We used global MHD simulation and reproduced a substorm by inputting the solar wind parameters during the reported event. The MHD simulation doesn't reproduce the precipitation process, but it can reproduce the magnetic field structure during during a substorm. And previous studies suggest that the condition for the field line curvature is indicated by the ratio between the curvature radius of the field line and the gyro radius of the particle. And these are the snapshots of this parameter for 100 keV electrons. And the regions where the condition is satisfied are drawn green or blue, and the maximum longitudinal extent was about 8 mLT, in other words, 120 degrees in longitude. And here we provide a rough estimation of the total impact area of the gross phase EEP using the observation and simulation result. In total, the spatial extent multiplied by the duration of the gross phase EEP events can be roughly a quarter of the EEP associated with pulsating auroras during recovery phase. This non-negligible contribution during the growth phase is missed in the EEP models depending on the geomagnetic activity indices such as AP index or AE index, because the growth phase EEP occur before a geomagnetically active period. And finally, I'd like to briefly show my current and future work about energetic electron precipitation. This figure shows the superposed echo powers to the onset time. And as you can see, before the onset, the averaged power was enhanced and at an altitude, at the mesospheric altitude. And the CNA intensity was slightly increased, so suggesting that the echo was associated with ionization in the mesosphere. These results partly support the non-negligible contribution of growth phase EEP, as suggested by previous event reports. And yes, sorry. Here I summarize my presentation, and we investigated on EEP event causing the mesospheric ionization during the substorm growth phase. And the spatial extent of the EEP was estimated to 8 mLT using MHD simulation. Considering the duration and the spatial extent of the growth phase EEP, we suggest that the total ionization impact can be non-negligible compared to during the other substorm phases like recovery phase. Okay, thank you very much.
Thank you very much, Kyoka. So we have, okay, so I think we're done with all our speakers of this session, but I'd like to maybe give a chance to Ryu Wang again, our first speaker, whom we lost due to some problem of connection. Ryu, if you're still here and if your connection has improved, can you share again? Yes.
Hello, Tony.
Yes.
Sorry, everyone didn't want to show the presentation again. She just finished.
Okay.
Yeah, she just answered the questions by Taguchi Nakamura. Yeah. Okay.
No problem. Just in case we missed some important points, and she wanted to have another go at it, just since we are doing fine on time and out of fairness. But if she's okay, then I think we've gone through all our speakers who were online. I think we had 2 missing speakers. I don't see their name, so I don't think we have them online. So it means we have about.
Sorry, I asked Dr. Fujia too, and he said he cannot be present now.
Okay, all right. Well, that's fine. In that case, it gives us a healthy time in case there is some open discussions that some people would like to start. this is a good time to address them orally, because the next session will start in about, let's see, 34 minutes. So we can either go to an early break before the next session starts, or if somebody has some questions to the general audience, some points of discussions, now is the time to speak up. So you can unmute yourself if you'd like to say something. If you have some questions to our speakers or to the broader audience, please go ahead now. So maybe actually, I have actually one question, because we've had a lot of presentations coming out of sort of a domain and the Chinese stations as a whole. It's obviously on purpose, since we organized the schedule of this session by time zone, so that Asia was first, and then we moved to different time zones until we reached the west coast of the US. But since we have a few PRIC people online, does anybody know roughly how the activities at domain will resume with COVID having hit every single polar institute and logistics having been hit accordingly? Does anybody have any insight on the resumption of activities and the pace of it? I'm not hearing anybody.
Hello, Tony.
Yes.
Actually, let me introduce shortly about the a situation. Up to now, Chinese expedition didn't go to DOP-A in over 2 years. This summer season, the expedition will be go to there. I think the probability is quite high, because they are doing some they're doing some logistic and some inventory documentations now. I noticed Michael has asked one question to G2 about the terahertz experiment possibility to install in Dome-A. He said the 39th January will be there this summer season. That's all my known about the situation.
Thank you. These kind of updates are really important to share around the community, because I think we are all aware that it's difficult to resume. I hear, for example, that that South Pole Station is not opening to new experiments until the end of the decade, so they can deal with the backlog of logistics and upgrades and things that were supposed to have taken place over the last couple of years. So I think it's very important for this community to really share all the information on the logistical hardship that is ahead of us still, because I think it will affect a lot of plans of new experiments, upgrades, and definitely affect how we do science from Antarctica over the next few years, possibly as far as long as the end of the decade potentially. So it's definitely important to share this information. So thank you very much for answering this.
You're welcome.
Question. Is there any more questions or comments from anybody online? I think nobody has anything. In that case, I'm gonna suggest we go into our break a bit early, but I think it's gives a chance for everybody to freshen up. We will resume on the hour. So I mean, I don't want to say which hour because we're all on different time zones, but in exactly 29 minutes from now, we will have our next speaker, Ryo Kataoka, starting the next session. Our session will be convened by Lucilla, Alfonsi, so we'll be more quiet. So I will see you guys in 30 minutes, almost sharp. I'm going to mute myself, and Lucilla will speak up when we are ready to resume. But otherwise, if you still want to engage with others, the chat is open, the Q&A is open. So if you want to communicate with each other, nothing is stopping us from doing so. Thank you.
People can help. I ask the first speaker to start to share the screen in order to save time. Okay, perfect.
Can you hear me?
I can hear you. I can see your slide
Right.
presentation mode. Thank you so much, Rio. We wait for a few minutes to let the people come in. So welcome back to our session, Astronomy and Geospace Observations from Antarctica. I'm Lucilla Alfonsi. I'm the pleasure to co-chair the session with Tony and Adriana and Jennifer, that is not attending today, but she helped us in the preparation of this session. So I will give the floor immediately to our first speaker. For all the speakers, as Tony was saying the previous slot, the Q&A space is available for discussion. Keeping time for the speaker, I will give you an advice when 2 minutes are left. So I'll give the floor to our first speaker that is going to present. Yes, Rio, the floor is yours. Thank you.
Okay, let me start. I'd like to introduce new Japanese Antarctic research project, which is called Aura X Cosmic in short. This is a 6-year project and just started last April. More than 25 Japanese researchers are involved in this project. And this project is Japanese JARE prioritized research project, and focusing on the space environmental changes and their effects on the Earth's atmosphere explored from the polar cap region. which is supported by NIPR. And we will study space weather and space climate from Antarctica to understand how the Earth's environmental system is open to space. The polar cap is a special region to study such a theme, and where the magnetic field is mostly open to the solar wind, and therefore the atmosphere is directly affected by various types of energetic particles from space, such as electrons and protons. We are interested in KeV to MeV electrons and MeV to GeV protons, which ionize the mesosphere and ionosphere, mesosphere, and stratosphere. We think international collaboration is very important. And auroras can visualize the atmospheric impact from such auroral electrons and solar protons. However, the auroras in the polar cap area are less understood because of relatively poor coverage of imaging observations. On the right-hand side, black circles show existing all-sky images, but gray circles show future possible field of view, which can be made by international collaborations. So we will be able to solve the technical problem by developing and distributing new images by international collaborations. And now we are developing a small, very small, tiny auroral image system, including a housing bearable for Antarctica environment. And this system will be low cost, low power, portable, and data will be obtained real time. And the first model will be tested in new Dome Fuji station next year. And they can be provided or distributed for other stations for future collaborations. So far, we identified two good wavelengths. One is red line 630, and another is blue line 391.4. For the red line 630 nanometer, we are interested in extremely bright large-scale auroras, for example, which occur during space weather events, such as very strong interplanetary magnetic field. Theta aurora giant spiral and space hurricanes are known, and which can be observed by this red line. And such extreme events will occur many times in coming solar max, which is expected in 2025. And for blue emission 391.4, we are interested in solar proton event-related auroras, which was surprisingly discovered at Mars recently. But it also can emit the blue line strongly on the Earth's polar cap area. Those MeV protons, and we are also interested in giga electron volt protons, which is related to radiation dose at right altitude. Such energetic protons can be observed by neutron detector or muon detector. Now, a global muon detector network consists of 5 stations, including Showa station. So at Showa station, we have muon detector and neutron detector. This is 4-year data, and associated with increasing solar activity, muon counts or neutron counts, which are related to 25 giga electron volt protons and 5 giga electron volt protons, respectively, show decreasing trend associated with the solar activity. we can use such data too. And also network data can be used to evaluate the radiation dose. So Showa station has such a neutron monitor, muon detector to observe the high energy solar protons. And during the Aurora X cosmic project, the cosmic ray observation Showa will be full system in 2024. And the real-time data will be obtained every 10 minutes. Also, Showa station has many geophysical observations, including superdome, pansy radar, radiometers, high-speed auroral imagers, and magnetometers. And also, unmanned network observations are distributed around all over via international collaborations now. And Aurora X project, Aurora X cosmic project will make such many kinds of observation data open to public. Now, global MHD simulation called REPU is also important, and which is now used as physics-based model for the reanalysis data study. This is a different project, but Aurora X Cosmic will provide the observation data set to this sister project. And this is an example of super down C cross-polar cap potential data. And this is ensemble mean of REPU simulation results. And the right-hand side panel shows the data assimilation result, test result. And also, the REPU simulation is now getting very high resolution. And this paper is the latest, just accepted yesterday, latest paper showing the high resolution results, reproducing small scale auroral arcs, such as sun-aligned arcs and fan arcs. So we are interested in the complexity of northward BZ polar cap dynamics by comparing the ground-based imager data and REPU results. So that's all.
Okay.
Yeah.
Thank you. I was saying 2 minutes left.
Yeah,
but you are
okay,
closing.
let me finish.
Sorry.
Final slide. Yeah, thank you. Yeah, I hope to collaborate with you all in coming 6 years. We have time. And if any question, please contact me. My name is Ryuho Kataoka at NIPR. That's all. Thank you very much.
Thank you, Rio. Can I ask you what are the timing you are foreseeing for these new deployments?
Okay. Are you asking about the camera system?
Mm-hmm. Yeah.
Okay. Yeah, this is almost ready, and next year we will test this camera system at around New Dome Fuji Station. Okay, so 2 years later, we can collaborate. We can provide the full system to anybody who are interested in to collaborate with us.
Perfect. Thank you so much. Very interesting. I invite all the attendees to discuss with you on the Q&A space. And I invite the next speaker, Hiroshi Matsuo, to share the screen. Perfect, Hiroshi.
Yes. Okay. Can you see the screen?
Yeah.
Okay.
The floor is yours. Thank you.
Thank you. So, well, I'm going to talk about our plan or the proposal of the terahertz interferometry in Antarctica. Especially this time I talk on the program on Dome Fuji, New Dome Fuji station. And with my collaborators who now are proposing the first 30-centimeter telescope at the site to be installed in a few years. First of all, I'd like to discuss the importance of terahertz observation and the angular scale of observation is plotted as a function of frequency. And in terahertz, which is 10 to the 12th, 10 to the 13th hertz, or 30 micron to 300 micron, the angular resolution is poor because because you have to observe from space using relatively small telescope. And on ground, you can use large telescope and interferometry. But terahertz observation was done. For example, an ionized oxygen line at 88 micron was observed by ALMA. Because the galaxy is at very high redshift, so the line is redshifted. But actually, it is not easy to observe the galaxy in nearby universe using terahertz emission lines. So that's what we want to make from Antarctica. So there is a terahertz gap here. So this is an example of atmospheric emission observed. This is the Chinese, based on the Chinese program using fully transformed spectrometer, which I collaborated. And this shows the best atmospheric emission obtained during the measurement, and which shows the terahertz windows, which correspond to ionized nitrogen and 2 ionized oxygen lines, and also the very important ice feature from protoplanetary disk, which would be at 43 micron. So from high site in Antarctica, Dome A and Dome Fuji could be the best site on Earth to observe terahertz emission. But the challenge for interferometer is atmospheric phase fluctuation, so the disturbance. The technology I talk is intensity interferometry. The intensity interferometry is a relatively old technology, but actually the intensity correlation is very stable against phase fluctuation. So if you can make images by intensity interferometry, it is very interesting. So the concept is like this. Using 2 terahertz telescopes, in this case, 2 30-centimeter telescopes, equipped with fast photon detectors, possibly photon counting detectors, and recording the data. And correlation can be made offline on the computer. So this system can be very flexible to make interferometry, because the telescope system can be independent to each other. So the baseline limitation, there is not much limitation on baseline length. But the problem is how to reconstruct the astronomical images. So you have to obtain complex visibility, which is the amplitude and phase of cross correlation. So we do not have a phase information with intensity interferometry, but we still have information of the photon stream, I mean photon bunches. So thermal photons are bunched, which make the intensity correlation. And the number of photons in terahertz is a lot. For example, it's from a relatively bright source. You can count 100 megaphotons per second. And with this number of photons, the delay time accuracy you can expect by counting these photons for 100 seconds, you can get accuracy of 0.1 picosecond delay time, which can be used to define and measure the delay time, which can be converted to phase information. So you can get complex visibility in principle. I can show one example we have done in microwave using Nobeama radioheliograph, which is a small telescope array observing the sun. And there's two correlation. Top one is amplitude correlation, which shows the fringing. The fringe is made by the phase information, the difference of the phase. And the correlation of intensity is shown on the bottom figure, which do not have fringe. So if even if there is a phase fluctuation, the intensity correlation should be stable. And you can even obtain the delay by fitting the the correlation. So you can get the delay. With 50 milliseconds of integration time, we could obtain an accuracy of 5 picoseconds, roughly. So it can give a delayed accuracy enough to obtain the aperture synthesis imaging. So we want to demonstrate, we are now trying to demonstrate the terahertz or submillimeter wave intensity interferometry in lab. This is a laboratory experiment setup, which is now really under construction. And most of the element is now ready to use. The collimating mirror, the cryostat, and the mirrors and the detector, which is SIS photon detector at 500 gigahertz, cooled by 0.8 Kelvin sorption cooler. Okay, so the plan is to bring the interferometry to the site in Antarctica in the new Dome Fuji station, which will start operation in the coming round of the expedition. And a general observing research program is now accepted to install the first 30-centimeter telescope with SIS mixer at 500 gigahertz. So our plan is to make another telescope, which is now under, we are now requesting budget for that program. And the telescope, this is the design of the first telescope to be installed in Dome Fuji, which is the 30-centimeter offset Cassegrain telescope with 5 micron accuracy, surface accuracy, so which is enough to observe terahertz wavelengths, even at up to 1.5 terahertz. And this is, which is equipped with SIS mixer receiver at 500 gigahertz with wideband IF frequency.
Hiroshi, 1 minute left.
Okay, thanks. So we are now planning to install another telescope to make interferometry. The second telescope will be mounted on a sledge, so it can be moved around so that you can change the baseline to make a different, to obtain higher angular resolution. Possibly up to 50 kilometers, around 50 kilometers between old and new Fuji, Dome Fuji stations. So this is the schedule at the moment. The first telescope will start observing in 2026. And we are going to install the second antenna in 2027 and hope to start interferometer observation in 2028. That's all. Thank you.
Thank you, Hiroshi, for the amazing presentation. And I invite all the attendees again to use the Q&A room to discuss with Hiroshi. And I invite the next speaker, Bima, to share the screen. Thank you.
Okay. Can you see my screen?
Yeah.
Okay, thank you. I'm Bima from.
Can you show in presentation your slides? Okay, perfect.
Oh, okay,
Okay.
thank you. Hello everyone, I am Bima from Sun Yat-sen University, and I'm going to talk about the daytime seeing at domain Antarctic. Last year in the SCAR-AAA meeting, I reported our results of nighttime seeing at domain. So this year I will talk about the daytime seeing. The first part is the introduction. I believe everybody knows this very well. So domain is the highest point in Antarctic plateau. So the seeing are expected to be very excellent. To measure the daytime seeing, our group developed a dim called the Kunlun dim, for short KL dim. It is special designed for domain to function correctly in this harsh environment, like -80 degree. We have some thermal design and mechanical improvement. And we also have built an 8-meter high tower. And, 2 KLDIMs were installed at domain in 2019, and they were fully automatic observed since January. And the data are processed in real time, and the seeing results are sent back every half an hour and showing this in our website. This is an example of seeing results showing the telescope worked very well, like 7 days, 24 hours. And even when the temperature dropped to 75 degrees, they also worked very well. Last year, I reported the nighttime seeing results, and here I just give a very brief summary. This figure is a histogram of the nighttime seeing in 2019. We can see that there are 3 components, log normal distribution in this histogram. They are the free atmosphere seeing, boundary layer seeing, and the intermediate seeing, respectively. This kind of distribution is caused by the variation of the boundary layer thickness. If the boundary layer thickness the boundary layer is very thin and our telescope is above the boundary layer, then the seeing is excellent. But when the boundary layer is very thick and our telescope is within the boundary layer, then the seeing was not so good. And our telescopes are located at 8-meter high. The free atmosphere seeing fraction was about 31%. For the free atmosphere seeing, the median value was about 0.31 arcsecond. So it is consistent with the result from SNODA before. For the daytime seeing, because our telescope is designed to measure both daytime and nighttime seeing, the daytime seeing was obtained between January and March. And excellent seeing, like better than 0.3 arcsecond, were measured, but there are also some bad things recorded. I plotted the histogram of the in January, February, and March in this figure. We can see that the histogram in these 3 months are quite different. The data point in January is not as many as February and March. But from this, we can see that the median value in January is about 0.9 arcsecond. In February, the value is kind of worse, about 1.2 arcsecond. In March, it is much better, only about 0.3 arcsecond. If we look at the daytime seeing at other sites in Antarctica, Qiguo just reported in last session the seeing at the daytime seeing at Taishan Station. We can see this. At Dome C, the daytime seeing median value is about 0.55 arcsecond. At Dome F, it is even better, about 0.4 arcsecond. So our daytime seeing from Dome A was not as good as expected. So we are still trying to figure out what's the reason. One kind of possible cause is the variation of the wind speed. We can see that from like 10 years ago to now, the wind speed at 4 meter or 8 meter high is raised slightly or significantly. So we are not sure if it is a yearly variation. In Qiguo's report, he also mentioned that the best seeing occurs during the dawn and the dusk at Taishan Station. It was also reported by the Dempsey group, but they only see the best seeing occur during the dusk. I plotted the daytime seeing versus the local time at Dome A for January, February, and March, respectively, too. And we can see that there is a local minimum of the daytime seeing around the dusk, but it is not as clear as other site. And even during the midnight, the seeing is also as good as the seeing at the dusk. So the behavior of daytime seeing at Dome A looks quite different with seeing at Dome C or Taishan Station.
2 minutes left.
Okay, thank you. From the daytime seeing, we also find the correlation between the seeing and weather information, including the temperature, wind speed, the wind direction. And we find that the major factor which affects the seeing most is the temperature gradient. In this figure, the axis was the temperature difference between 8 meters where the telescope was and the surface So we can see that when the temperature difference exceeds 10 degrees, the seeing is around 0.3 arcsecond. This indicates that the boundary layer is below 8 meters. So we can use the temperature difference as an indicator of the boundary layer thickness. The wind speed also plays an important role. This was also found by the Dempsey group. Lastly, the summary. Our KLDIM was successfully operated at Dongmei, so we get both the daytime and the nighttime seeing. The nighttime seeing was very excellent, as we expected, while the daytime seeing was not as good as we expected. So we need more data to confirm this. Our DIM suffered from some issues of ice or frost. So we are considering some de-icing solution to improve this. So hopefully this year we will go to Dongmei again, and we can make our KLDIM work again to get more data. So that's all. Thank you.
Thank you, B, for your presentation. Thank you. Once again, use the Q&A chat to discuss with the speakers. I ask to Jianjun Liu, sorry for my bad pronunciation, to share the screen and for the presentation.
Okay.
Okay, perfect. We can see perfectly. The floor is yours.
Okay, hello everyone. I'm Jianjun Liu from Polar Research Institute of China. I'm going to talk about a transient response of polar cusp ionosphere to an interplanetary shock sudden impact. It is known the large-scale optical auroras are large-scale optical aurora features associated with the solar wind discontinuities displayed some dynamic features such as the aurora immediately brightens near local noon, and the intensified aurora enhanced firstly in the around the cusp regions, and then propagate along the dusk side and downside to night side ionosphere. This is the typical large-scale aurora response to the solar wind discontinuities, and simultaneously ionospheric plasma convection response to the solar wind discontinuities, such as interplanetary shocks or enhanced solar wind dynamic pressures, also shows the significant plasma flow features such as enhanced convection strength and appeared intense downward convection fluxes around the cusp and morning side. Recently, prompt and complicated plasma flow reversals just after the IP shock arrival to the Earth space was also reported, especially in post-noon and evening sectors. And we want to know the transient ionospheric azimuthal convections, and especially the vertical ionosphere in response to the interplanetary shocks, because it is known that the polar region as an open window for the Earth space to interplanetary space plays an important for the solar wind and Earth magnetosphere interaction. So the polar ionosphere is very important for the mass and energy interactions and transportation in the solar wind and magnetosphere and ionosphere coupling systems. The Yellow River Station and the magnetically conjugate Zhongshan Station in Antarctica, due to their higher latitude location. So both stations its priorities to monitor the cusp reaction to the solar wind discontinuities. Here, I just want to show one example by using the Arctic Yellow River Station located in the Svalbard region, to monitor an ionosphere and optical aurora response to the interplanetary shock impact. It is shown that the solar wind discontinuities propagates over 40 minutes to the Earth's base and then trigger a typical sudden impulse or sudden commencement. Just after that, the geomagnetic field perturbation occurred, and the optical aurora showed very dynamic features in diffuse uniform aurora structures and discrete manifested as rays and curtains structures. So this kind of diffuse aurora response to the shock instantly and propagate power. And simultaneously, the high latitude ionospheric convection also shows the typical summer plasma flow from the multi-cell ionospheric plasma convection patterns. This is one example to show in the cusp ionosphere in response to an interplanetary shock compression. Here, I just want to show one example by using the Antarctic Zhongshan Station space measurements. Here, the Zhongshan Station was carried by the one superdome radar in McMurdo, and actually, the Zhongshan Station also carried by the superdome radar in Silva East, but due to the lower data quality for this event, I just show the superdome radar of Zhongshan and McMurdo. Just during this event, the Zhongshan Station just locates on the magnetic local known region, so which is supply a very good chance to monitor the cusp ionosphere in response to the solar wind discontinuities. Here it is showing the solar wind and interplanetary parameters for this interplanetary shock event. It is noted. It is worth noted to the IMFBC component. The IMFBC before the IP shock was acquired and around 0, and just after the IP shock, the IMFBC was further positive, and simultaneously the solar wind plasma data shows the sudden enhancement, and after that, the geomagnetic field from the high latitude to low latitude region shows the very typical geomagnetic response, geomagnetic measurements. And this is the ionospheric, the digisound observations in the Zhongshan Station. It is the sky map which shows the horizontal and vertical plasma drift. It is clear, just clear to show the before the IP shock arrival to the Earth's base, the plasma environment over Zhongshan Station was relatively quiet. Just after the IP shock compressed to Earth space, the plasma over Zhongshan Station showed a prompt downward motion, just as shown in this panel. And simultaneously, the ionospheric profile just showed the new enhanced sporadic ES layers around 110 kilometers. And this is the ES profile parameters. To investigate and to verify the simultaneous ionosphere reaction to the interplanetary impact, we also checked the magnetical Yellow River station barometer data. It is showing the prompt increased ionospheric absorption, and simultaneously.
2 minutes left.
Okay.
2 minutes.
Okay, this is the Superdown Zhongshan radar. The number density profile. It is showing the decreased number echo numbers, and this is the satellite over Zhongshan station, which shows the electron density and the ion fluxes before the IP shock arrival. This is the just after. It is clear showing that the enhanced electron and ion fluxes, and simultaneously the DMS satellite over South Pole region also observed the enhanced ion fluxes. And here we show the high resolution Superdown radar data in Zhongshan station, and this is the McMurdo radar observations. Both of the radars also observe the simultaneous plasma flow reversal caused by the interplanetary shock region. And here is the large-scale plasma convection. We can see the plasma flow pattern changed instantly just after the IP shock arrival. Here is a schematic illustration of electric field, which drives the plasma flow reversals and a downward motion of the ionosphere. Here is the conclusion. We show the ionosonde Zhongshan in Zhongshan station detected sporadic ES layers and vertical plasma motion following arrival of an IP shock to the Earth space. And the evidence suggests also the sporadic ES layers are the result of intensified particle precipitation, which observed by geomagnetically conjugate barometer. And the IP shock triggered sudden impulse alters the dusk to dawn electric field that drives a brief downward plasma motion at polar ionosphere. That's all. Thank you for your attention.
Thank you a lot for your amazing presentation. Thanks so much. Use the discussion room for posing questions to the speakers. Okay, next speaker is Mehmet Otken. Please, Mehmet, if you can share your screen.
Hello, can you see my screen now?
Yes, not in presentation mode. Okay.
Okay, and what about now? Can you see the presentation or the on it? Wait, let me.
Is still not in presentation mode.
Wait a minute, I'm sorry. All right, maybe this. Wait a minute, I'm so sorry. Okay, now I think you can see.
Yeah, perfectly. Okay. The floor is yours.
Okay, thank you very much. In this presentation, I'm going to present a presentation on the effects of solar zenith angle to the peak height of F2 layer of ionosphere on the Antarctic station, Zhangpogo. During this presentation, I'm going to divide my presentation to 3 parts. First, I'm going to give you some background information about ionosphere and Chapman production function. And then I'm going to share our results. And then, of course, I'm going to give my last thoughts about my conclusions. We believe that examining the effect of solar radiation, which is the main cause of ionization of ionosphere in the less studied Antarctic regions compared to Arctic regions, So we tried to connect the solar zenith angle with HMF2, which is one of the most important aspects of Chapman function. And we used Jank-Bogos station during 21st December of 2019 to 21st March of 2020, which is the solar Antarctic summer. So during these dates, the sun will be always on sky. So we think that it might be suitable for investigating the solar zenith angle with HMF2. So let me say something about the ionosphere. Of course, we all know ionosphere is the upper layer of atmosphere, and it's quite important for propagation and reflection of radio waves. And it's not certain, but it begins in 60 kilometers and ends around 1,100 kilometers in normal regions, not in Arctic or Antarctic regions. And it's reached its maximum around 14 local time, because it's changed due to time and your latitude and the season. And it consists layers of D, E, F1 and F2 during daytime, and it's at nighttime, there's only E and F layers you can see. And there are polar regions, middle latitude regions, and equatorial regions, of course, of ionosphere. And especially the polar region is quite important, because it's affected from solar wind and the magnetic field of Earth. So it's quite a complicated region to investigate. And that and especially the Antarctic regions are less studied than Arctic regions. Antarctic ionosphere is slightly different than the ionosphere that I talk about. Of course, it's very sensitive to magnetic disturbances, because it's the closest place to magnetic field lines. It's different than the normal ionosphere regions. Its maximum values of FO2 is around 6 UTC during Antarctic summer, which was 14 at other regions. And its daily variation depends on, especially by natural winds. And the Chapman production function is a formula that which helps us to predict electron density profile of ionosphere, and it's got 4 main assumptions. First of all, it says atmosphere is composed of single species, which distributed exponentially, and the second is there are no any variation in the horizontal plane, which means the atmosphere is plane stratified, and the solar radiation is absorbed by concentration of gas. And the last assumption is the absorption coefficient is constant, which means the radiation is monochromatic. And here is the function, is a Chapman production function. And from some calculations, we can easily get the maximum height of the peak height of FT region by this formula. You can see the kappa is solar zenith angle. So when the sun is at the top, that means HMF2 is the highest point. We used the times between 2019 and 2020, which are the beginning of solar cycle 25th, which is the quiet conditions. And these are our KP and the SC indexes. So you can easily see there's no even there is no any middle geomagnetic storms. So it's quite calm conditions, you can say. So we used Jank-Bogos station which is located at right there. And you can see the graphic of solar zenith angle during the times that we investigated. After 10th of February, the sun will set at that point, so you will see. These are our HMF2 values. There are so many missing values, but it was quite important for us to investigate even in these conditions because our analyzed data is quite big. So here we plot a graphic in x-axis. You can see the solar zenith angle, and y-axis you can see HMF2. So you can easily see as solar zenith angle increases, the HMF2 increases too, and there's an exponential, and you can say it's quite looks like an exponential increase. And you can see there's a gap between two data sets. And this is because of it's going to, I mean, the sun sets at 90 degrees, so we try to delay these data. So our analyzed dates changed a little bit to 21st December to 10th of February. And since it was a little bit complicated to try to make some assumptions due to this graphic, we did some mathematics. We take averages of we take weekly averages to see the effect of solar zenith angle, which HMF2. And here it is left and up graphic. You can see the first week, second week at the right top, and so it's go on. So you can easily see when solar zenith angle increases, the HMF2 increases too, which is quite same with the Chapman
2 minutes
function.
left.
Okay, thank you. And in our 5th and 6th, and it's same for all weeks, but it's not quite same with our aspects with Chapman function. And you can see it's always increases as we expected. There are no any suitable data between 22 of February to 29 of February. But especially between 15 of February to 21st of February, it's quite complicated graphic. It's not, I mean, it looks like another polynomial function. Anyway, so thanks to our graphics, we can easily see that HMF2 increased as the solar zenith angle increased, as we expected. But the Chapman production function may not be efficient for Antarctic ionosphere during the times that we investigated. But we cannot say anything certain yet. So we are going to examine more data, more stations, and more different times to say something more certain. So these are our acknowledgements. We take our data from OmniWeb, NASA, and NOAA, and of course our ionosound data from Lovell Giro Data Center, and we also thank to that Polar Research Institute. Thank you for your attention. I would like to answer your questions.
Thank you, Mehmet, for your presentation.
Hello, everybody. I will share the screen. I cannot start screen share while the other participant is sharing. Then please.
Yes, the page stopped sharing, so you should be able to share your screen now.
Okay.
Okay.
I hope you can properly see the presentation now.
Perfect, Alberto.
Okay, many
you
thanks.
You can start. Thank you.
Yes, I am Alberto Pellizzoni from the National Institute for Astrophysics in Italy, and I will present the development of this new project, a new observatory, a solar observatory that will perform solar imaging, mostly devoted to space weather science and services. This project is developed by a quite wide collaboration in Italy, including National Institute for Astrophysics and many universities, including radio astronomers, solar physicists, and also people experienced in operation in Antarctica. The idea is to obtain an observatory that can perform solar imaging at high radio frequency, around 100 gigahertz. It's a smart solar monitoring system in the, because it will exploit mostly existing instrumentation and knowledge. For example, we can implement this system on existing small radio telescopes in our laboratories in Italy, and even in the existing facility, for example, the Mario Zucchelli station, and so on. We are presently in the development stage of the receivers, state-of-the-art receivers based on ALMA technology. And also we are exploiting innovative technique that we successfully applied for the large Italian radio telescope for sun observation. In Italy, we are developing a quite wide network of assets for space weather using the radio band. And in particular, I am the PI of the Sun Dish project that use the large antenna in Italy, even the Sardinia radio telescope that is 64 meters large antenna, in order to observe the sun. The system has strong limitation, as I will show you soon. Powerful but strong limitation due to the sun visibility and observing condition. Then the Solaris Observatory is placed, for example, in Antarctica, will allow us to perform a very huge step forward in solar monitoring. The technique that we use for the observation in Italy, it will be the same that we are willing to implement in Antarctica. In this case, you can see in the left part of the plot that there are our images at 18 and 26 gigahertz. You can find information about our investigation on a recent paper on solar physics and also on a dedicated web site. Why is so interesting to observe and monitoring the sun in the radio band? Using this quite innovative single dish imaging technique. It is important because even in well-known observed astronomy frequency ranges, there is a lack of information. There is a gap of information in the radio band concerning the sun observation, even for the observation of the quiet sun, as you can see here in the plot, in which there is it showed the brightness temperatures of the sun as a function of the frequency. There are gaps, there are scattered data. And so thank you to single dish observation, we can have calibrated images of the sun. But the most important thing that also we could extend this, thank you to the Solaris project, this idea to higher frequencies where the scattering of the observation is higher and there are no continuous monitoring of the sun, only sporadic. Most important is the fact that we observe the dynamic chromosphere. Then we can observe and characterize the spectra of the active regions. Okay, usually active region could have, for example, a thermal spectrum, but sporadically they could have a strong gyromagnetic components. And then we can investigate a sudden spectral change of the active region And after such event, typically a flare can occur a few hours or even a day later. Then you can see that this imaging technique could provide a very useful tool for space weather, not only space weather science, but also services, forecast. Okay. This project has a strong limitation, as well as the other sun observation. We can observe only on a weekly basis at better, and other instruments are slower, even less. Then we cannot actually monitor the sun as we like to do. Okay, and this is because the idea of Solaris, because if we implement you can find here all information about the existing and present observation activity of the sun. I told you that Solaris could offer unique key points. For example, we can observe during the Antarctic summer for about 20 hours per day. And the Solaris Observatory will be the only solar facility offering continuous monitor at 100 gigahertz. Then, since we can use at higher frequency, very small radio telescope, 2 meter class, it's feasible to use our technology there in Antarctica as well as in Arctic in order to monitor the sun continuously. The best place to use our technology is, without doubt, Antarctica. We perform some investigation about the implementation of the system, for example, at the Mario Station. Obviously, it can cover part of the year. Ideally, in perspective, could be also an implementation of the system also in the Northern Hemisphere. In this case, we'll have a full coverage and monitoring of the radio sun for all year long. This is just a simulation of the image quality that we can reach using small radio telescopes and smart and also relatively low-cost systems. In any case, even with these simple systems, we can reach a very interesting resolution of just a few arcminutes, and we can see the evolution of the active regions, study the spectrum of the active region, because we simultaneously observe in dual frequency. Then we can also spectral imaging and look for flare, and also correlate flaring events with changing precursors in the sense of changing of the spectral characteristics of the active regions. Then will be a continuous monitoring of the sun. And this is
Alberto, 2 minutes left.
Yes, thank you. And this cannot be achieved by present larger and expensive instrumentation that we have in Italy. We started to this idea to observe the sun with the radio telescope, Italian radio telescopes, in single dish mode a few years ago, and now it's a consolidated project. But we can go on true solar monitoring only if we implement little systems operating at high frequency in Antarctica. That's all, and thank you for your attention. Obviously, if you're interested in collaborating, we are pleased to share our knowledge and our work on that. Thank you very much.
Thank you, Alberto. Also, Alberto Pellizzoni is waiting for you in the Q&A room for discussion. So there is a change in there was a mistake in the list of speakers. Stefano Sartor is going to give the next presentation. Stefano, are you here? Yes, I can see you.
Yeah, can you hear me?
Yeah. Please try to share your screen.
Okay, can you see my screen?
Yes, and we see the scheduling. Okay, perfect.
Okay.
Thank you.
Thank you. So I'm Stefano Sartor, and I'm working in the Aosta Valley Observatory. I will talk about the upgrades we performed on the ITM telescope. You can see here the structure in glass-like, and the boxes and all the upgrades we installed in the last summer campaign. The focus of the new upgrades was to simplify all the components and to give each functionally isolated component a single box. For example, we have here on the mount the control box, which is in charge to give to move, for example, the focuser, or to give commands to the motor box to move them to steer the mount. We have the motor box, which which contains the power electronics for moving the motors, and the delicate component of the slip ring, which is in charge of rotate the power for the telescope, and also the signal, the land signal, which permits to communicate with the shelter and also through the internet. This was a delicate component which stopped the telescope for 1 year for refurbishment. Now with the newly designed, very simplified design, we can, which is under assessment right now, we can say we can operate, and we can also substitute the components without dismounting all the telescope with very less downtime, such as the previous occasion. We also have the power distribution box, for example, and then the LAN, the network box. Here we have an example of the motor box. As I said, one function, one box. So we have the power electronics for the motors, a simple electrical management by a PLC, and a thermal management. Then we have the connections for in the external, which you can see. If you can read the labels, they say just motor, heating of the motors, and for example, I/O connection such as the joystick and the elevation limits, and also the encoders. It might seem naive to you to, like I said, one function, one box, but it's we found the hard. We learned the hard way this lesson, because during the winter time, when fails occurs, you need to specify to put the box on the shelter, as you can see here, and for repairs, and doing it outside is very uncomfortable. Another upgrade we did is the software upgrade. Again, we switched for a command line based software to a fully fledged, fully featured graphic user interface. This allows the user to have a lower learning curve, and to perceive all the system as simpler just by having buttons instead of a keyboard, for example, for commands. Again, this might seem a normal approach, but the functionalities we have now and compared to what we have then were the same. Where they're just organized in a nice way, in order to let the user to approach the software with without any fear. We also have this new software allow us to integrate, for example, Python scripts for automatic schedule of the observations, and also we have a web client, so the user during the winter rover can just, for example, look at its smartphone and go to the website page of the instrument and see what's going on, if the telescope is moving right, if it's doing the job, if for example, if the schedule is on time, if there was any sort of problem, thermal problem whatsoever. Another very nice feature we implement, on the left side, you can see the old configuration. So we have the axis encoder, then we have the encoder reader, then the software was reading from the encoder reading the position, and then was calculating the movement of the sky, and then feed the electronics of the stepper motors for the axis with the commands. The critical part here is the timing, because from the communications from and to the driver on the PC and done by a LAN connection, okay, an Ethernet cable. So we need to take account of the various delays which affected the precision of the appointment. Now we have a closed loop approach. So the new electronics is capable enough to read by itself the encoder position and then provide a feedback of the position to the motor with the corresponding action. For example, we have a PID algorithm to install in the firmware on the motion controller and in the motor electronics, which gives us error correction in the position. Within this technique, we are measured a precision of pointing measured on the encoders in about 0.4 arc seconds, which is well within the precision of our encoders. Finally, we have an early result. Right now we are in the commissioning phase. Here you can see the pointing model, and at the bottom of the slide you can see the equations we use for this pointing model. The dots, the colored dots, are the points of synchronization. So the plate solved by software, and in the color scale indicates the error of measured between the encoder and the sky position. The background color is the correction which with the pointing model can apply to the mount. So the goal is to match the color of the background with the color of the synchronization points. I think we're doing the early results are quite promising, and we hope to conclude the commissioning phase by the end of the winter time, so we can start. We can be back in business, as they say, for science and next winter campaign. Thank you for the attention.
Thank you, Stefano, for being time. And I invite everybody again to discuss with Stefano about his presentation in the Q&A room. The next speaker is Alessandro Liberatore. Alessandro, are you here? Alessandro, I see you in the list of attendees, but I cannot hear you. Alessandro? I don't know if it is only my problem, but I cannot hear Alessandro.
No, me neither. I think it's on Alessandro's side.
I don't know if the IT team can help if Alessandro has some trouble. Okay, maybe we can go ahead and try to reconnect Alessandro after the next speaker. Wojciech.
Can you hear me now?
Alessandro, yes, very weakly. Alessandro, are you here?
Can you hear me? Yes.
Yes, okay. Please share your screen.
Sorry for. Okay, can you see my presentation?
Yeah, please, the floor is yours.
Okay, now in full screen, I think. Okay, good morning, afternoon, evening, everyone. I would like to show you some results from the Extreme Solar Coronagraphy Antarctic Program experiment, so the ESCAPE project. In particular, this project was performed in different Antarctic campaign, in 3 different Antarctic campaign. And in a nutshell, what we obtained and what we are going to see in this presentation is the first results from this project. And we can see, for example, how we validate a new coronagraphic site, so a new place on Earth where it's possible to observe the solar corona, and where the solar corona is the outer part of the solar atmosphere, as we will see. Then we will see also the first coronal signal observation from Antarctica, and then a characterization of a micropolarizer camera that is used for this observation. First of all, for those who don't know what the solar corona exactly is, as I said, is the outer layer of the solar atmosphere, is mainly composed of 3 different components, K, F, and E. We are interested in the K1. The K1 is obtained by the Thomson scattering of the photons from the photosphere to the free electrons in the solar atmosphere. And it results to be linearly polarized and tangent to the solar limb. So to fully study the solar corona, we need, for example, the Stokes formalism that is necessary to study, fully study polarimetrically the solar atmosphere. This Stokes formalism consists in retrieve 4 different parameters, E, Q, U, and V, that is possible to obtain with 6 different polarizations, 0, 90, 45, and 135th, and 2 different circular polarization. Now, as said, the K corona is linearly polarized, so we are interested just in the first 3 Stokes parameters, E, Q, U, and so we need just 4 different images as 4 different polarization angles. Thanks to them, we can combine, for example, the Q and U parameter to obtain what we will see and we will call as polarized brightness, and also the degree of linear polarization, the OLP. The solar corona has a brightness level that is very low. As we can see in the previous plot, the brightness in function of the solar disk brightness decreases very fast and is at the order of 10 to -6 times the brightness of the solar disk. So this means that the brightness of the solar corona is 1 million times less than the solar disk. For this reason, we need to occult the solar disk signal to be able to observe just the coronal signal. To do this, we use a particular instrument called coronagraph. We can see here an example. We use an internal occulted coronagraph. So the solar disk signal is focused on an internal occulter that works as a moon. And then while the solar corona signal is focused through the detector, through the telescope to the detector. Now, it's not necessarily just a coronagraph, because as we can see in the previous plot, the sky brightness is high enough to cover the signal from the solar corona. So with the coronagraph, we can block the disk signal, but we still have the problem of the sky. For this reason, we need to go in some particular place. Today, it's just one place has the sky characteristics that give the possibility to observe the solar corona, and this place is that Mauna Loa Observatory. And part of this, of the goal of the SCAPE project, is to find another place where it's possible to observe this corona that is useful, of course, for the space weather and to better understand the Sun-Earth connection. This place is Concordia Base. We thought that Concordia in the Dome Sea in Antarctica, in the middle of Antarctica, had all the characteristics to be a good coronographic place. We have also the possibility to have the sun 24-hour, 7 days, and this gives also the possibility to observe the sun with more continuously than in Mauna Loa Observatory, for example. Moreover, Concordia is a very dry place, one of the driest places on Earth, and we are far away from any kind of pollution, anthropic and not. And there is also an advantage due to the atmospheric thickness, because we are at 3,300 meters above sea level. This is Concordia Base, and as said, we performed this during 3 different campaigns, the Italian campaigns, the 34th, 5, and 7. And to do this, we used the Antarctic, so the Antarctic coronagraph that we previously calibrate in Turin. And you can see here some of its features. We observe in the white light in 545, 605 nanometers. And the peculiarities of this telescope is the use of this polar cam. The polar cam is a CCD detector with a grid or micropolarizer with 4 different orientation angles. In this way, with a single shot, we have the 4 images at the 4 different polarization angles that we need to obtain the Stokes parameters that we talked about before. So with a single shot, we can fully characterize polarimetrically the solar corona. Of course, there are many problems in Antarctica. One is, of course, the temperature and also the diamond dust. For the temperature, we can deal with the temperature thanks to some heaters, but for the diamond dust, we have not yet a solution. So when there is this diamond dust, so ice crystals in atmosphere, that can also polarize the light, so can create several problems to polarized observation. We are just not able to observe. So we can look at some sky information through other instrumentation to see if we are able to observe the solar corona or not before start observations. We can see here an example of sky brightness evaluation. Has said to be a coronographic site, we want a sky brightness, B sky, of the order of 10 to minus 6. And in this way, we know that the site is coronographic, so the brightness of the sky is lower enough to give us the possibility to observe the solar corona. We can obtain this value through a ratio
Alessandro, 1 minute left.
Okay, a ratio between an image of sky and an image obtained with a diffuser. More information you can you can find more information on this paper. And you can see here the results. In 3 different campaigns, we can see different colors. What we obtain is that the sky brightness is indeed at the order of 1 to the 10 to -6. And this definitely say that Concordia base is a chronographic site. These data were obtained fixed heliocentric height, but we performed also the same study for different, for example, declination and right ascension, obtaining again results that confirm that the sky is chronographic. We can see here the average results from the 3 campaigns. So we are from 0.7 to 1.2. And this is the first observation of the solar coronal signal. Of course, we need still to work on this, but we can compare with what observed by, for example, Mauna Loa, the blue one. And as you can see, seems that the signal is pretty consistent with what observed from Mauna Loa. So the red one is consistent with the blue one. And so this is what we talk about. In the future, we want to validate also a space project that is based on these structures, on the structure of these telescopes. And we need also to improve for sure some the results obtained through the PolarCam detector. Thank you for your attention.
Thank you so much, Alessandro. And the next speaker and the last one for this lot is Wojciech Milok. Wojciech, are you okay? You're sharing.
Yes, I'm here. I hope you can hear me. I hope you can see me. And then I hope you can see the full screen as well.
Yes, everything is working.
All right, thank you.
Okay.
Good. Thank you very much, and welcome everybody. I'm gonna talk about ionospheric plasma structuring over Antarctica, which is based on satellite and ground-based observations. So we all know, or most of us know, present in this session, that the magnetosphere, ionosphere, and thermosphere coupling is a very complex system, and this is also illustrated here on this picture, showing all the interactions between that is happening in the MIT system due to the interaction between the sun and the Earth. So this interaction, which is not only magnetical, drives a multitude of physical phenomena, and this coupling is, in fact, and associated effects are most pronounced at high latitudes. As you can see here, we have the auroral oval, we have the convection pattern, and we have the auroral particle precipitation that we have heard of already during this session. Also, in these regions, we have the highest structure, we have the high structuring of ionospheric plasma density. The other region where the high ionospheric structuring occurs is in fact in the equatorial regions, but this is due to different processes and different instabilities. These irregularities in the ionospheric plasma are quite important for in the context of the space weather, and as they also impact the propagation of transionospheric radio signals. But this affecting of the transionospheric radio signals can also be used to infer the structuring of ionospheric plasma. And one of the examples that is shown here is related to the polar cap patches. Polar cap patches are the regions of enhanced plasma density that are traveling across the polar cap with the convection pattern. And while they are traveling across the polar cap towards the night side of the auroral oval, they get structured and at their edges. And this leads to significant increase in the rate of change of tech and also the elevated phase scintillation indices. Here's an example of the all-sky imager data from the Arctic, in fact, from the Ålesund, showing also the overplotted phase scintillation indices. And you can see that they are quite high at the edges of the polar cap patch that is traveling towards the night, towards the nighttime auroral. But we can also detect patches, polar cap patches with the satellite in situ measurements. And here's an example of the measurements of the polar cap patches using the SWARM satellite mission, where we have the 3 SWARM satellites that are detecting the in situ. They are detecting the plasma density using the Langmuir probes. And you can see that the patches are traveling and they are across the polar cap, and also they are becoming quite structured. So based on this fact that we can have a very good coverage with the satellites, we can carry out the statistical study. And we have developed algorithms to detect the polar cap patches with this SWARM satellites. And the results of the statistical study is quite interesting, because you can see that in the northern hemisphere, the polar cap patches are distributed quite evenly over all magnetic local times and latitudes, while in the southern hemisphere, there are more observations of the polar cap patches in the on the day side, and they are also on the evening side. So this is also reflected in the overall climatology study, where we have the studies of the occurrence rate in the northern hemisphere and the southern hemisphere. We can see that while we have on average the increase of the occurrence of the polar cap patches in the local winter, in the northern hemisphere, we do not basically observe any polar cap patches during the daytime, but in the southern hemisphere, we have the significant occurrence of the polar cap patches also during the local summer. So that's a difference that is also related to the offset of geomagnetic poles, and it leads to the difference in the structuring in the ionosphere on both in both hemispheres. For addressing the structuring of the ionosphere, we use the EPIR, the ionospheric plasma irregularities data product that has been developed for SWARM, where we have used different parameters such as rate of change of plasma density, the gradients, and the amplitudes of the gradients that are detected by SWARM. More details about the SWARM EPIR data product can be found in the recent publication in JGR by Yachijin et al. So let us now move to the results. And the climatology of plasma irregularities in the polar regions is very different in the north and in the south. In this upper plots, we are showing the results from the Langmuir probe measurements, and also from the GPS measurements on board of SWARM satellites. So this is related to the topside ionosphere, total electron content, rate of change of tech, and rate of change of tech index. While on the left-hand side, we see the plasma density, the rate of change of density index, and the gradients in the plasma density. And what is striking here is that we have a significant difference between the northern hemisphere and the southern hemisphere. Immediately, we can see that the southern hemisphere, which is the bottom row, is much more structured and much more turbulent, I would say, as compared to the northern hemisphere, where most of the structuring is happening in the auroral oval, which is denoted here as for KP3, and then we also have contribution due to the cusp and the Tonkov ionizations and the polar cap patches. So significant differences also in the structuring when we look at the seasonals. We can see that the RODI is different between the north and the south. They are a little bit off, but while we can see the out of phase plasma density that is shown here in the top panel, we can see that when it comes to the structuring of the ionosphere, the north and south, they are quite similar, but southern hemisphere, which is shown with the straight lines without dots, it's much more structured as compared to the northern hemisphere. Of course, this structuring is changing with the activity of the sun, and here we can see the declining solar cycle activity and how different parameters are changing. So the plasma density is changing and also is decreasing in the polar cap in the north, and consequently we also see smaller gradients, smaller RODI and ROTI indices as the solar activity is decreasing, and the same is observed for the southern hemisphere. So now, having in mind that the plasma structuring is different in both.
Wojciech, 1 minute left.
Yes, I'm trying to speed up. So having in mind that we have the different structuring in the north and the south, we also are using the ground-based measurements. And in particular, here we are using the Troll Ionospheric Observatory at the Norwegian Research Station Troll in the Dronning Maud, where we have installed all-sky imagers and GIST receive. And here we can observe that the elevated scintillation indices, which are associated with the structuring of the ionosphere, can be associated also with the flow shears at the edge of the convection pattern during the substorm expansion phase. And that's the study between the Troll and Sana'a stations in the Dronning Maud. This is also observed, similar behaviors observed in the Northern Hemisphere conjugate points over southern Greenland, where we are not showing the scintillation data here. So here we have the magnetometer data, and we see the substorm and associated scintillation indices, which are related, which can be related using the SuperDARN data with the flow shears. And this is also confirmed by the DMSP satellites that on that day were crossing over the both stations. And indeed, even in the in situ data, they are showing that we have the very strong flow shears observed during this expansion of the auroral oval. And the last slide is shown here that in the coming years, we are a partner within the Troll Observing Network project, which will last for 10 years. And through this TONE project, we plan to deploy the ionosonde to study the ionospheric structuring and its dynamics in greater detail at Troll. But we also, in addition, plan to install a magnetometer. So there's more things to come in future. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Wojciech. And the Q&A room is for discussion. We are now approaching the time for the break. So I wonder if Tony and Adriana would like to say anything. Otherwise, I will quit this part of the session and leave the word to Adriana for the next slot.
Yes, I would like to remind you that the dynamics of the last part of the session will be the same as this one. You will have 10 minutes. I will give you 1 minute warning before the time, and I will and you will be able to ask questions to the presenters in the Q&A facility. So that will be the dynamic. Thank you.
So I thank you all the speakers again. And the break is 10 minutes time, if I'm not wrong, Adriana, and then we will reconvene.
Yeah.
Okay.
See you in 10.
Thank you.
I will just pause the recording and resume it when we start again in 10 minutes.
Okay, so we are back.
Hi.
Hi, we have Silvia Massi, and she will talk about spectral distortions of the cosmic microwave background from Dome C.
Do you see my screen?
Yes, perfect.
Oh, okay.
The floor is yours.
Sorry? Yeah, thanks. So I'll speak about COSMO, Cosmic Monopole Observer, which is dedicated to the spectral distortions of a CMB, Cosmic Microwave Background Radiation monopole. And these are a unique way to study several processes, as you can see here, happening in the different epochs during the evolution of your universe. And only upper limits exist at the moment at the millimetric wavelengths, and they are of the order of 100 parts per million. Obviously, the final instrument, the final measurement requires a space mission, but pathfinders are really needed to develop and test the instrument configuration and to detect the largest part of this distortion, called the Y distortion, which is due to the presence of ionized matter in the post-recombination universe. This amounts to, this is 50 times smaller than the current upper limits. And what I'm reporting here is a staged effort called COSMO, as I said before, with the first implementation in Dome C, at Dome C, Antarctica, and the following one, which will be a stratospheric balloon mission. As I said before, spectral distortion of the CMB monopole are very small with respect to any other isotropic backgrounds, including instrument emission, atmospheric emission if present, astrophysical foregrounds from the interstellar medium and the other galaxies along the line of sight. And the CMB monopole itself, so the instrument has to be a cryogenic one to reduce its own emission, and has to operate where the atmospheric emission is very small or can be measured and subtracted. So COSMO is a cryogenic differential Fourier transform spectrometer, so a differential instrument, comparing the brightness of the sky to the brightness of an accurate internal back body, exactly like the Cobiphyras was in the 90s. So you can see here on the left figure the optical configuration of a generic DFTS. So one input port looks at the sky and the other one at an internal calibrator, and assuming the emission of internal calibrator is accurately known, the measurement of the absolute brightness of the sky is obtained by inverse Fourier transform of the measured interferogram, which is described by this first equation. The calibration constant is measured closing the sky port with another accurate black body radiator. And on the right, you can see a figure of how the DFTS is implemented inside the COSMO cryostat, and details will follow later. So with COSMO, we have to cope with atmospheric emission. So COSMO will operate from the Concordia French-Italian base in Dome C in Antarctica, which is one of the best places in the Earth from this point of view, and uses fast detectors, so kinetic inductance detectors, which have a time constant of about 50 microseconds. And this allows us to use fast elevation scans to separate the atmospheric emission and the long-term fluctuation from the monopole of the sky brightness. So there will be a fast spinning wedge mirror, which is steering the bore sight direction on a circle about 20 degrees in diameter, scanning a range of elevations and the corresponding atmospheric optical depth, while the cryogenic interferometer scans the optical path difference. Here is a simulation of a single measured interferogram, which is obtained by scanning slowly the optical path difference between the two arms of the FTS, while the wedge mirror is spinning fast, so that for each optical path difference, we have at least one sky dip down and one sky dip up. What you can think is that you can think of this interferogram as many interleaved interferograms, one for each elevation scanned by the instrument. So in this way, if you resample the interferogram with the appropriate phases, you can retrieve the interferograms corresponding to the different optical depths of the atmosphere and extrapolate to zero air mass using a cosecant law. So you can see here at a single frequency for the interferograms at different elevations, you can retrieve the spectral brightness versus optical depth. You use a cosecant of elevation law, and you can extrapolate the sky brightness, which is cleaned this way from atmospheric emission for each frequency in the covered band. This is just naive end-to-end simulation of this kind of procedure, assuming the measured spectrum of the atmospheric emission fluctuations in dome C and 1 year of integration of our instrument, which produces the result that you can see here for the spectral measurement of the spectral distortions. The spectral Y distortion is, in this case, well detected. Obviously, it takes 1 year. What we are doing together with Lorenzo Mele, a postdoc working with us, is to make a more detailed simulation with respect to this naive one. Here you can see barely see, I must say, the top level schedule of the project. We are almost here. You can see we are in the middle of a fabrication of the subsystems. So what I'll describe now is the instrument configuration and the main subsystems. As I said before, the instrument is a cold interferometer inside a large dewar, large cryostat, a cryostat using a pulse tube. This cryostat is the same as the cubic, similar to the cubic one, which is now operating in Argentina. And spinning wedge mirror is not shown in this picture, but is mounted on top of a vacuum window. Then there is a large absorbing for baffle, which is protecting the spinning wedge from stray light. The interferometer operates at 2.7 Kelvin, and the optical path difference modulation is obtained by translating one of the two roof mirrors by means of a frictionless cryomechanism, which is actuated electromechanically. This is how the instrument will operate. This is the cryostat. I'm not sure you see my mouse. Anyway, the red thing inside the container mounted in on the yellow stand is the cryostat, and we need a 20 kilowatt energy for 100 days at Dome C. This is just to show that the pieces of the cryostat and the various pieces, which are very similar to the cubic ones, and the cryogenic DFTS is requiring this cryomechanism, which is able to move back and forth the roof mirror, which is also shown in the bottom left figure. This cryomechanism is based on a voice coil to push or pull the mirror, and this mirror is suspended through flexible stainless steel blades, so that the mechanism is totally frictionless, apart from the eddy currents, which are in any case minimized by using the electric coil support. As I said before, the kinetic inductance detectors are the detectors we choose, and they inherit our experience with Olimpo stratospheric balloon flown in 2018 from Svalbard. We will use two small arrays of detectors, and we will use, in this case, multi-mode feed horns also in aluminum. This is a scale. This picture shows a scaled version of a black body, and the simulation made with HFSS provide a residual reflectance of about 3 × 10⁻⁶ at 120 gigahertz, and this is the prototype is under test at the moment. The future of Cosmo is after 1 year or more of measurement to validate the method and to characterize the systematics of the instrument at OMC is for sure something that is going to be a long duration balloon telescope, and then later, years from now, when I'll be retired, something like a satellite mission. For doing
1
this,
minute.
yes, thanks. I'm almost done. So these balloon simulations of a balloon integration time of 10 hours brings you to a very good detection of a Y distortion in 10 hours. And this comes from a feasibility study carried out within the Cosmos project funded by our Italian Space Agency, and the synergic effort, same kind of goal, the scientific goal is done by the French with Visu stratospheric balloon. So conclusions are these: Cosmo is the first attempt at millimetric wavelengths to measure the spectral distortions of a CMB monopole from the ground. It beats the atmospheric noise and measures the atmospheric emission by using a fast modulation and fast detectors. And if the strategy is effective, the sensitivity is enough to measure the Y distortion arising from quantization and recombination and reionization. It then paves the way for more accurate measurement with the same approach to be carried out on a stratospheric balloon and later on a satellite mission, and can and should be complemented with low frequency monopole spectral distortions like the Tenerife microwave spectrometer or array of precision spectrometers for the epoch of resonation APSIRA. So I thank you, and I'm done.
Thank you, Silvia. You can ask questions to Dr. Masi in the Q&A facility, and she will jump on writing the answer.
And I stop share, right?
Yes. Next speaker would be Maria Marcucci. She will talk about cross-polar cap evolution during the geomagnetic storm of 25 August 2019. The floor is yours. You please share your screen. Thank you.
Thank you. Can you hear me? Yes.
Yes.
Yes. So cross-polar cap potential evolution during the geomagnetic storm, and I would like to specify that I'll do it using super DARN data. My name is Maria Federica Marcucci. I'm from the National Institute for Astrophysics in Italy. The cross-polar cap potential is an important parameter that helps study the solar wind magnetosphere ionosphere interaction. This is clear when we look at the what happens in the magnetosphere when the interplanetary magnetic field is southward. When the IMF is southward, reconnection occurs at the dayside magnetosphere. We have that magnetospheric closed flux opens. Newly reconnected and open magnetic flux tubes are convected anti-soundward, accumulating the tail where reconnection occurs again. And so that reclosed flux tubes convect back to the dayside magnetosphere. These convection anti-soundward and then again soundward correspond to anelectric convection fields, and also that is projected in the high latitude ionosphere, and also at the soundward motion in the anti-soundward motion in the polar cap and return flows at lower latitudes. This actually gives rise to the typical ionospheric convection cell, and this is typical for the steady state, of course, when a reconnection at the day side and then the night side in the geomagnetic tail is balanced. If, for example, reconnection is ongoing only at the day side magnetosphere, we have the polar cap potential, that is the drop between across the polar cap, is equal to the voltage drop across the day side magnetosphere. And the opening of the flux give rise to an expansion of the polar cap. The other way around is when the reconnection is going on only in detail. So it is clear that this cross-polar cap potential is an important parameter, and there have been numerous studies about this CP. A lot of them has evidenced that this cross-polar cap potential saturates in case of strong solar wind driving. And the CPC can be also estimating using the Superdan data. In fact, it is the voltage difference between the center of the evening and morning ionospheric convection cell. And because Superdan data, as you probably know, actually, most of you know, is able to image the ionospheric convection. This is possible because each radar of the network, you can see here a typical field of view of one of these radar, is able, by analyzing the ECOS backscatter by the ionospheric irregularities, to measure the line of sight velocities of such irregularities that are frozen in the ionospheric F region plasma at several distance from the radar site, typically 75, and at along 16 different directions. Having two radar with our overlapping field of view, we are able to measure actually, when we have backscatter from these irregularities, the two-dimensional velocity of the ionospheric plasma. So having sufficient number of radars both in the northern and southern hemisphere permits to have an imaging of the ionospheric convection and the time resolution of the Superdan observation that is typically 1 minute. In recent years, Superdan coverage has expanded, has improved a lot from mid-latitude to polar cap latitude. For example, one of the last radar that has been installed in the northern hemisphere, it has been a mid-latitude radar, the Chinese radar Jiangxi. And in the southern hemisphere, the last radar to be installed was a polar cap 1, and it has been installed in Domsi actually. So Superdan radar coverage has improved, and in particular for the geomagnetic storm of the 25th of August, we also we also have a lot of backscatter data. So we decided to look at the storm and see how the cross-polar cap potential evolves during the storm. Here we have in the three above panel of this plot the interplanetary condition. At a certain time during the 25, the IMF turns southwards so that efficient reconnection is activated at the day side of the magnetosphere. After a while, there is a storm, which is here described by the CMHE index. So if we look at the super-dark maps during this period, we have in the above row the super-dark maps for the northern hemisphere, and below the super-dark map for the southern hemisphere before the beginning of the storm and before the southward rotation of the IMF. Then we have some plots during the evolution of the storm. So you can see actually what happens. The ionospheric convection both in the north and in the southern hemisphere intensify after the southward turning and during the storm. And also we see that the polar cap expand, comparing this to the area of the polar cap before the storms. As I said, we wanted to study the cross-polar cap potential, so the potential drop across the center of the two cells, and we concentrate on the northern hemisphere for this plot that I will show you. And actually what we did was that we compared this, what is observed by super-dark, that is the blue line here, to two models that explain the saturation of the cross-polar cap potential in different ways. The two models are the Cisco-Hill model and the Kivelson-Riedel model, which are the black, which are the black lines and the red lines. These two models are theoretical models which depends on the electric field of the solar wind and on the Pedersen conductivity and Alfvén conductance. And these two models, as I said, explain in two different ways the reduction of the saturation of the cross-polar cap potential. The first one, the Cisco-Hill model, explains this as due to a reduction in the day-side reconnection rate, while the Kivelson and Riedel model explain this saturation as due to the partial reflection of the Alfvén wave in the ionosphere, which reduce the transmission of the signal from the solar wind to the polar cap. So in the Kivelson and Riedel model, it is the ionosphere who plays a role in this saturation. So what we can say when comparing these two theoretical models with the super-dark measurements. We have that overall, I will only highlight some points, not all the features that can be seen and discussed. Overall, we have that the cross-polar cap potential measured by super-dark is very similar, or I have to say the other way around. The theoretical model resembles the evolution of the CPC as measured by super-dark, except during before the geomagnetic storm and after, when the super-dark cross-polar cap potential is higher than the predicted, probably because these two models do not take into account that besides reconnection, there also a viscous interaction between the solar wind and the magnetosphere. During, after the southward turning on the IMF, the evolution is similar, apart from an interval in which the cross-polar cap potential differs from both the two models. And this interval, interestingly, correspond to a plateau in the
1 minute.
Thank you. Yes, I finished to the plateau in the CMH index. And overall, actually, it seems that the cross-polar cap potential is more similar to the Kivelson and Riedel model. So here are my conclusion. We study the cross-polar cap potential with the super DAN, and we compare it with two models. Apparently, the better agreement is with the Kivelson-Radley model. We have an interesting feature that deserves further study. The cross-polar cap potential in the southern hemisphere that I did not show, but we look at also, is generally lower, which cannot be explained here as a seasonal effect, because we are almost at the fall equinox. The important thing this is a preliminary study, because we have to take carefully into account two things. One is that this model use a value, an estimated value for the Pedersen conductivity, and that also the CPC as measured by super DARN is different from it is the CPC as measured by the spacecraft different. So we have to look carefully at these two things to draw a quantitative conclusion of what we have observed. Thank you. I finished.
Thank you, Maria. Dr. Benjamin Schmidt, the floor is yours. Please make the questions to Maria in the Q&A question.
Well, thank you so much. Hi, friends. My name is Benjamin Schmidt. I'm a project development scientist at the Harvard-Smithsonian Center for Astrophysics. It's my honor to represent the BICEP Tech collaboration to talk briefly today about instrumentation and polar infrastructure development supporting the BICEP Ray telescope, which is aimed at probing the cosmic microwave background, or CMB, from the Amundsen Scott South Pole Station in Antarctica. So why are we at the South Pole? South Pole offers an unparalleled platform to probe the CMB in our cosmic origin. Now, just as a brief review, when we talk about the CMB, we're talking about a relic light from around 380,000 years after the Big Bang, where the CMB was generated at the point during the evolution of the early universe, when the universe expanded and cooled to transition from a hot, opaque, dense primordial plasma of coupled photons and baryons to an environment of decoupled photons and neutral hydrogen. The decoupling allowed for photons to stream away, forming the CMB signal that we measure today. That's enabled a rich array of scientific discoveries, including probes of the evolutionary history, composition, and dynamics of the primordial universe and the growth of structure today. In the case of the BICEP array experiment, our team is testing the inflationary theory of the early universe, driven through the measurement of constraints to the tensor to scalar ratio known as R, where at full deployment, BICEP array will measure primordial gravitational waves to a precision of sigma R between 0.002 and 0.004 after a full 3 years of observations with over 30,000 detectors on the sky. But again, you might be asking, why the South Pole? And this is really important. CMB science from the South Pole offers an unparalleled observing condition, one of the premier sites for CMB science on the planet, a high altitude site with extremely dry, stable atmospheric conditions, which offers the ability to target the so-called southern hole, which is a region of the sky that's exceptionally free of dust and synchrotron foregrounds in the galaxy in total intensity, which allows for unmatched conditions for conducting CMB science from Earth's surface. And this is an important point, and this is exactly why the BICEP Ray telescope is being built to make precision measurements of the polarized cosmic microwave background and to constrain galactic foregrounds, drawing on the heritage of 5 generations of small aperture telescopes that have been operating at the South Pole for more than a decade. Now, in particular, BICEP Ray is comprised of 4 receivers deployed on a single telescope mount with wide frequency coverage to do just that, to constrain galactic synchrotron at 30-40 gigahertz, galactic dust at 220 and 270 gigahertz, and then having our primary CMB channels at 95 and 150 gigahertz. So looking very briefly at the technology that's already been developed as a part of the first already deployed BICEP Ray receiver deployment, the 30-40 gigahertz receiver that's aimed at measuring galactic synchrotron foregrounds. This receiver, known as BA1, can be seen in cross-section on the left here. And it really is, it's comprised of a lot of very important technologies. Cryogenic refrigerator systems, cryogenic optics, and detectors that have drawn on the strong technology development heritage of the BICEP Tech program that you saw in the previous slide. The BA1 receiver is cryogenically cooled using a custom helium-4, helium-3 sorption fridge, providing an operating base temperature for a focal plane of 250 millikelvin, which on the lower right, you can see in this inset, dual polarization antenna coupled transition sensor detector arrays, where the detectors are read out using time domain multiplexing with a multi-channel electronic system. And on the upper right, you can see the primary cryogenic optics that comprise the BA1 receiver and the optomechanical subsystem, including two 637 millimeter diameter high-density polyethylene biaspheric optics, planar nylon filter, where each of the optical elements feature an anti-reflective coating to mitigate reflections that we find in band, and an Echozorb set of Echozorb HR10 absorptive cryogenic baffling, all of which operate at 4K. So it took a lot to get here, but with BA1 integrated and well characterized in North America, the bicep array mount built and tested at the University of Minnesota, which you saw, you can see on the left here. That work then concluded in the summer of 2019, and so that in November of 2019, the austral summer of 2019, the deployment of both the bicep array telescope mount, which replaced the existing Keck array mount, as well as BA1 receiver, took place at the South Pole, which got us all the way to this image that you saw. You can see it here on the right in February at the end of the deployment season. So it was an enormous effort that took us to get through that summer season, and we were able to do that successfully as a team. So during this 3-month window during the Antarctic summer, our team and contractors were able to complete this mammoth set of tasks to first demolish the existing Keck array telescope mount, integrate and bring into operation the bicep array mount for the first time in the field, and then complete the assembly of the BA1 receiver and integrate that BA1 receiver into the mount itself, and basically perform tests that got us to science operations beginning in early 2020. And of course, it was well worth the effort. You can see here some of the early results demonstrating the system's successful operations. In this case, a 40 gigahertz temperature map of the CMB from BA1, covering 570 square degrees on the sky over the last observing season at Pole. Now, what's next? We're currently working hard on completing the other 3 bicep array receivers, which we're hoping to deploy to the Pole as soon as possible. The next of those to go down, of course, is BA2. A 150 gigahertz receiver, which you can see here, where the team is undergoing final integration and testing work at Caltech, and this should just go down to the South Pole in just a few months' time. When deployed, the BA2 receiver will feature a total of 7,776 TES detectors, utilizing that SQUID TDM readout that I mentioned before. And in closing, I want to take a brief look at the future. Our team is hard at work developing a project known as the Bicep Array Replacement Tower, or BART, which is aimed at extending a sustainable future for bicep array science operations. As you can see on this, back at the first slide of this presentation, the current bicep array tower and its attached laboratory building, which you can see down in the bottom right in illustration here as well, and that's known as MAPO, they need to be raised to snow grade. They're getting buried by snow. And they need to do that in the near future so that the deployment of the BART tower will allow for continued bicep science operations while we raise that facility, basically moving science operations over to that tower. And while new, BART is really a straightforward evolution of existing facilities and technologies, and it's being specifically designed to make use of a limited footprint that's consistent with the scale of existing facilities at Pole. In other words, efficiently using space, power, snow clearance, and other support elements based on heritage programs. So as we speak, the BART project design and development is well underway by folks here at Harvard CFA, the Smithsonian Institution, and having inputs for engineers with polar infrastructure experience, a team at the Cold Regions Research Laboratory, and of course, benefiting from key support from the National Science Foundation and ASC. And we're making great progress. The structural and civil designs are complete. They've passed final design review with construction set to begin soon. While the construction of the BART telescope mount itself, compatible with both bicep array and future CMB S4 small aperture telescope operations, is underway at an engineering firm in Italy. And simultaneous to this effort, we're also working to design provisions for the installation of solar arrays on the exterior vertical surfaces of BART, which draws from an Arctic precedent. You can see here on the bottom right, the 30 kilowatt vertical panel solar array that was deployed on the Australian Antarctic Division's Casey Station in 2019. So we're trying to do that to get about 10 kilowatts of summer power average. And again, this is point of use. So we'll have this independent of the broader South Pole Station grid. And that will hopefully allow us to save about 5 kilowatts per season. And just a very final closing slide to say that both the BICEP array receiver technologies that we've seen and are developing, as well as BART itself, they all serve as a pathfinder for a new program called CMB-S4, in particular small aperture telescope facilities at the South Pole. And that's going to be covered in more depth by my colleague, Dr. Miriam Diericks, later in the session. But at a glance, CMB-S4 will comprise 21 telescopes split between the Amundsen Scott South Pole Station and Chile's Atacama Desert, one large aperture telescope at the South Pole, which you can see on the left of this slide, and then 18 small aperture telescopes on the right. They'll be arranged across, they'll be arranged across 6 receivers at the South Pole, and basically include 150,000 superconducting detectors that span all of those frequency ranges, from the foreground operations to the CMB measurement operations, a fully cryogenic refractive optics, and 100 millikelvin superconducting focal plane, where the base temperature is provided again by that shared dilution refrigerator system in each receiver. So you can see some of the key technologies at the bottom: the receiver in the mount with the DR, and then the entire assembly inside of a double diffraction criterion designed ground shield, which you can talk about more in the questions. But again, this will all be covered in more depth by my colleague Miriam Diericks later in the session. So thank you so much, and appreciate all the work that everyone's doing for STAR, and look forward to any questions. Thank you.
Thank you, Dr. Schmidt. Questions, please, in the Q&A facility. We welcome Dr. Huang. Would you please share your screen?
Yeah, and I'm not the doctor yet, so just a student.
Okay. Future doctor.
Okay. Yeah. Okay, so my name is Wei Chen. I'm a graduate student in University of Chicago. So I'll talk about microwave astrophysics with the South Pole Telescope. So this beautiful picture was taken by a man who is currently living at the South Pole, operating the telescope. So as Dr. Schmidt already mentioned, so our universe started with very hot dense state, in which only there were free particles, quarks floating around. As the universe expanded and cooled, neutrons, protons were able to form, and as the universe cooled even further, we had atoms and then galaxy stars. So at around 400,000 years before that, there were dense soup of protons, electrons, photons. They were interacting with each other. Photons couldn't travel far enough. But after that, neutral hydrogen formed. Photons no longer interacted with electrons. So we have this freely moving photons. That's a cosmic microwave background, which was hotter, but now it's at the microwave region. So if we measure the microwave, we see this beautiful black body spectrum, which Dr. Masi has already mentioned. If we measure at each frequency, if we measure the intensity distribution, we see a uniform background, and then we see a and then we have typo. After that, we have these small scale fluctuations, which have been measured very well by 3rd-generation satellites. And in addition to intensity, CMB is also polarized. This is a plot on intensity over date on polarization. And so you can decompose these polarizations into these symmetrical patterns called E modes, or these curly patterns called B modes. And these are sourced by different physical mechanisms. So these CMB fluctuations, what are the causes? So as I mentioned before, photons were able to travel freely. There were oscillations among photons, electrons. There were gravity and pressure balancing each other, oscillations. So these fluctuations tell us what happened there. And after CMB formed, as it traveled to us, it also was deflected by gravitational lensing. So it can tell us about what happened after as well. And when it interacts with galaxy clusters, it gets its energy boosted. So from the original black body spectrum, you get the shifted black body spectrum. So at some locations, you see dark spots, some location you see some bright spot. And then, so you can measure those fluctuations in terms of spherical harmonic transform. And if you can plot the power spectra, and then you can fit various models of cosmology to them. And so you can learn more about our universe. And so the CMB intensity power spectra have already been measured very well by the Planck satellite, but the polarization measurement polarizations have not been all that measured well. And so there are lots of ongoing projects, ground-based telescopes measuring this power spectra to better precision. So if we can do that, for example, it can shed some light on this so-called Hubble constant tension. So this is a current open question, which is about some discrepancy between different measurements methods of this Hubble constant, which quantifies the current expansion rate of the universe. So the results from CMB kind of disagree with results from using what we see in the local universe nearby. So that's interesting. By doing better measurements, we can shed some light on this problem. And then also, as Dr. Schmidt mentioned, if we can measure this B mode better, then we can learn more about the very early part of the universe. So in addition to cosmic micro background, which is a dominant component on microwave sky, if we look at the map in a grayscale, we can see these bright spots, which are these emissive stars galaxies. So by studying the population and looking at how their brightness changes, so we can learn more about the physics of these objects as well. So yeah, so the microwave sky provides us with a lot of information, has a microwave background, dominant component, and we can also learn a lot of things about the stars and galaxies from microwave. Yeah, so one of the experiments that's doing these things is the South Pole telescope. So South Pole, as already mentioned, dry atmosphere, very little precipitable water, so ideal for microwave observations. So the South Pole telescope was built in 2006-07 Austro summer. It has a 10-meter primary mirror, so that gives us an Archimedes resolution, which allows us to both study those galaxy cluster stars, and in addition to measuring the fluctuations to small angular scales. It's been operating for more than 15 years with a lot of publications and citations. And so here is a kind of like a movie time lapse showing, maybe not working. That's fine. No, skip. Okay, here you go. So the telescope scan back and forth, measure the sky. Okay. So this is kind of cross-section of the instrument. So the light ray comes, reflects off the primary mirror, and then it goes into this refrigerator cryostat. And then at the bottom, there is a detector array light sensors. So we've had 3 generations. The third generation 3G was a big improvement from the previous one, with 10 times more detectors. So we're taking data with this currently. And in 2017, 2018, we worked very hard on getting the instrument operate to the optimal way. And we've had a pretty good data taking season since 2019 with stable operations, stable noise levels. And so the right to plots showing that if I look at data for only a couple of days, then it becomes noisy. But over time, if I take more data, then you have better looking maps. And so we are observing this small region of sky. We observe it multiple times every day. We do this couple of years so that we can get very clean, low noise maps. So we recently published some data using results from 2018, and so there's Dutcher et al., Park and Ho et al. So we used 2018 data. We measured those fluctuation patterns, power spectra, and so here it showed, and then from these power spectra, we were able to fit different cosmological models and deriving different cosmological parameters, such as the Hubble expansion parameter mentioned earlier. So we were able to improve our previous measurements. So from SPT-4 second generation 3G, you can see the error bars shrank by a good amount.
Wrap up, please.
Yeah, and then we'll have later you'll hear a talk about number analysis. So currently there are lots of projects ongoing using more data, 10 times more data, 1920 with so exciting projects going on. We're also collaborating with BICEP programs. And then we are also developing next generation instrument for what comes after 3G. So I guess to summary, so the microwave sky provides us with a wealth of information about the universe. And the SPT-3G has been operating for more than 15 years. We are currently taking a lot of data. A lot of exciting projects are ongoing. So that's all I have. Thanks for your attention.
Thank you, Juan. We welcome Dr. Chirkin. Would you please share your screen? And the floor is yours.
Hello, everyone. I will tell you about the work that we're continuing to do on ice calibration in our ice cube detector at the South Pole. Last year at this conference, I've already shown some results. Well, we've been working on this for a while. So last time I've shown the results on the birefringence of ice that apparently is an effect that is very tiny. You may not even have heard about it, but as the light goes through many thousands of crystals per meter of travel, it builds up to a very substantial effect that I discussed. And so we can actually see variation in the light output at 125 meters away from light sources in the ice cube detector by a factor of 2 or so. So that was a very measurable effect, resulted in an interesting measurement of like crystal size versus depth and things like that. So to remind you, I guess, or to introduce here, ice cube detector is a kilometer cube of a detector that is occupying space in the South Pole ice at depths between 1,500 and 2,500 meters. And it consists of more than 5,000 optical sensors, so we call them DOMs, digital optical modules, on 86 so-called strings. Yeah, so there we go. Each of the sensors contains a PMT that is sensitive to individual photons and from charged particles propagating through the ice and creating a chunk of light. But also, of course, we have for calibration purposes to measure the ice properties and calibrate the DOM optical module sensitivities and things like that. We have this 12 light emitting diodes in every optical module that are able to work independently or in tandem. Here is an example of such an event where 6 of the horizontal LEDs were flashing simultaneously, creating this huge event that is visible through much of the detector. You can see hundreds of optical sensors receiving light. So we have 5,000 sensors, 12 LEDs per sensor. That's 60,000 or more LEDs that can individually work, and we receive light on hundreds of optical modules around them. So that is a very rich data set, and we are able to do so much work with this. So that's why the work continues. Before the strings were lowered, when the detector was deployed, in 8 of the locations, we also lowered so-called dust logger. that is this device shown here. It emits a light in very narrow beam, goes into the ice, scatters around, and is received at the PMT at the bottom. The received signal is proportional, or depends very largely upon the scattering on the dust particles at the place where the light goes into the ice. So because of the thinness of this beam, we're able to resolve features on a like 2 millimeter scale. And here you see this optical signal recorded in 8 different locations across the detector shown here, color-coded. So you can use this, for example, to correlate this with the dust core data collected elsewhere in Antarctica, and we can use that to date the ice, and that has been done successfully. We know like how old the ice is. But also what's relevant for this talk is you can see that at different locations, for example, black here and here, and in this brown color on the other side of the detector, if you go focus yourself on this feature here, you can see that it is at different depths. So that was our first indication that the ice layers across the entire detector, because the detector is so large, I guess, are not flat. So especially at the bottom, this specific feature varies in depth by as much as 60 meters across the detector. So we can take that dust log data and plot it against the optical ice that was calibrated with the LED system that I mentioned, and you can see that they follow each other rather well. We have done this in published papers. In fact, we have another paper coming that discusses what I told you about the ice anisotropy and the crystal birefringence and things that I discussed last year. So to put things on a single plot here, you can see the ice, as you have seen, the layers at this location of string 50 and on the other side of the detector are shifted. And the main shift happens in this gradient tilt direction across the detector that is northeast to southwest, and indicated here by this line. But there might be also some tilt in the other, like in the other direction, I guess. And that's what we're trying to figure out here. There's also this the fact that the ice flows in the direction of the ice flow, which is indicated by this arrow here. It goes in a roughly perpendicular direction, and that's the direction that we've seen this anisotropy mainly manifest itself. So as the ice, I guess as the ice flows in this direction of the ice flow, it is forced across like this bedrock and features of the bedrock that are not, is not obviously not flat. So it kind of averages out as you go higher and higher in depth, it averages out those features as it flows over them, because we know at the surface the ice is flat. So so I guess it makes sense that the main gradient direction of the ice features at depth that we see, like intermediate depths of the ice cube detector, are somewhat perpendicular to the ice flow. Anyway, as I've mentioned, there is some deviations from the gradient direction of the tilt. So we've started the campaign of trying to figure out the individual ice layer deviations from the model that we've been using so far, by basically taking the ice model that we already have and shifting it, the ice table of parameters, and shifting it up and down around the individual DOMs. And here you see examples of several, like 12 is a string, 4 is a number of the optical module on the string, and they range from 1 to 60. So here you see just a few examples of those fits, and you can see that we can in fact figure out the individual shifts of the ice table in the vicinity of individual DOMs, optical modules. You know, that the points are spread around rather, you know, there is some stochastics to it. So we do need to do some more things to it. Like, for example, here I show how we smooth it. We smooth it both on the individual strings to kind of enforce the fact that the ice layers should probably maintain roughly, you know, more or less be nearly like like the thickness. So they shouldn't just dramatically deviate in the thickness. So that's one of the regularizations. Another one is that we want to try to smooth them out over the 3D space. So we've done that. And then we also built a model based on just grid of points that roughly matches the outline of the detector. And we interpolated, extrapolated to those points. Like here would be extrapolation, this individual tilts. So once we've done that, you do a combined ice and tilt table fit. And that is actually still ongoing. And I will show you a preliminary result at the end of this talk. So basically you take all of the data, all of the variables that we have. So that would be like you have 80 grid points and you have one reference point in this detector, which is near the center right here, where all of these tilt shifts are 0 by definition, and you multiply by a number of depth points, and then you have 3 ice parameters: scattering, absorption, and anisotropy strength, which is basically crystal size correlated to crystal size, multiplied by number of depth points in our ice table, and you arrive at this huge number of variables that you need to fit simultaneously to your flasher data. As I've already said, our LED flasher data is extremely rich, so we can actually carry this out. But because of number of variables, and because we're trying to work on at the limit of like what's possible statistically, you do have to do a number of tricks that have been developed over this last year or so. So basically, you have to enforce like positive definite nature of the probability that you're fitting, and impose some regularization. A number of them actually establish a basis of regularized tilt models that you can work with and things like that. But it is been worked out, and I think it's working rather well. And we are building something like this. So at the depth of the detector, you can see this model. The regions outside of the thank you. This is my last slide. The regions outside of the detector hexagon are extrapolations. Inside, we build this model, so you can see that you can see the gradient direction kind of going, like especially this is the bottom of the detector, and it will disappear shortly. So you can see that was the gradient direction, and then but there is also you will see that there is slightly more blue at the bottom right of the plot, and slightly more green at the top left of the plot, and that's this additional component that appears to us that the ice is being flowing downhill in direction to in a direction to toward top left, but there is more blue at the bottom right. So it's actually it feels like it seems like the ice is being pushed slightly uphill here. So that's interesting. I mean, we are not making too much of it yet, and we're still trying to figure this out. But this is the model, and it seems to be working rather well. And we're still working on this, and I think there will be a publication soon about that. Thank you.
Thank you, Dr. Turpin. Now we welcome Dr. Kurahashi. Maybe, can you please share your screen? And the floor is yours.
Wonderful. I hope I'm well heard. And
yes.
Let me just make this full screen. Thank you. Okay, so I'm here to talk about neutrino astronomy in IceCube. I'm here very much on behalf of the IceCube collaboration. That's me at the geographic South Pole, where IceCube is located, as you have heard. We do a lot of different science in IceCube. You've heard in the previous session, Tepe Katori talk about beyond standard model physics that you can do with IceCube. I'm here to talk about the astrophysics side of the collaboration and its results in this talk today. So as Dima Churkin has already explained, that picture of me at the South Pole, I'm actually standing on 2.8 kilometers of ice. It is actually high altitude at the South Pole. I got altitude sick, so it's hard to think that you're on top of a mountain actually when it's such a flat, large glacier. But if you think about digging down 2.5 kilometers and installing light sensors, over 5,000 light sensors, each of them about yay big, it's a huggable sort of size, a barely huggable size. I mean, it's a huge undertaking. I say numbers like 2.5 kilometers, but I always remind people, like, try to pick a direction and run 2.5 kilometers. That's a really long way. Now think about going down that way. I mean, you can understand the sheer scale of this experiment. And of course we did this, and people like Dima studied the ice properties carefully for us because we're trying to look for neutrinos. So neutrinos would go in, they won't emit light. And if they detect in or around the detector, they would produce particles that emit light. And because the neutrinos we're looking for are very high energy, the particles that they produce will have that directional information preserved. So from that, we can look back and figure out where the high energy neutrino came from. And that's kind of the core principle of IceCube astronomy. You need neutrinos and you need to point back to look at the sky. So again, a huge undertaking, deserves a huge collaboration. We're about, I think 35 institutions, something like that. I think it's about 14 countries. I'm sorry, I keep losing count of this, but this is our most up-to-date collaboration map, so you can see who's involved here. So let me tell you first about the Crab Nebula. Well, not really. I just want to tell you that it is a star with a gas cloud around it, because this is an astronomy session. I wanted to anchor us somewhere. So we know that it's a star with a gas cloud around it because we've seen the Crab in radio, ultraviolet, optical, and X-ray. And this is the same part of the sky, but looked at in different ways, right? So this is what is known as multi-wavelength astronomy. You have the radio, the UV, optical, and X-ray. These are all light but different wavelengths. So this would be multi-wavelength astronomy. What IceCube is trying to do, as I mentioned before, is really to see the universe in neutrinos. So now this is not a different wavelength of light anymore. This is a whole different particle. So this is what we would call multi-messenger astronomy. So we're trying to see the universe in neutrinos. And if you think the night sky, when you look at it with your own eyes, and you know your own eyes are an optical detector, so you see optical light and you can see stars and maybe galaxies and other things. It's that kind of map that we're trying to recreate in neutrinos. So that is the main mission of IceCube, is to recreate the sky in neutrinos. And why would we want to do that when we have perfectly fine messengers? So it's because of this. So this is a plot where the y-axis is the distance from us and the x-axis is the energy. And as you get to high energies, you don't have those photons that reach us anymore. All of a sudden, you can't see things anymore because of the infrared and microwave background that has been talked about. The high energy photons will interact with them. So this shaded region, you cannot probe with light. And in fact, this is kind of even a little bit generous, because in places where high energy photons, gamma rays, are produced, it's probably a situation where there's a lot of stuff around in gas clouds, what have you, and gamma rays have a hard time escaping that kind of environment because it just wants to interact. So it's very hard to see the high energy universe using light. So multi-wavelength astronomy is great, but at some point it gets extremely difficult, especially if you want to see far away. So neutrinos don't have this problem because the property of neutrinos, as Tepe Katori said in the previous session, is that they're ghost particles. They don't interact. So we should be able to see deeper and higher energies in neutrinos. And then there are cosmic rays. We've seen cosmic rays at even higher energies. But the problem with cosmic rays is that we know they exist in very high energies, but they have charge, so they deflect in the magnetic field around us and between us and other galaxies. So they don't preserve the direction where they came from. So the neutrinos, we hope, would serve as the gap between gamma rays and cosmic rays in terms of energy, but also in terms of the resolved sky of gamma rays, where we know where these gamma rays are coming from, and these high energy cosmic rays where we can't tell where they are coming from. So that's the goal. I say that's the goal, but until 2013, we said this, and we hadn't ever seen a high energy neutrino from outside our Earth or outside the solar system. And so 2013 was really the discovery of the diffuse emission of neutrinos. So this is when we got the cover of Science in 2013. Here is our 2013 discovery plot. This is events in this 2-year period versus energy. This is an energy plot. The purple is all the backgrounds of things we know are there, and the upper limit of things we think are there added together. And you can see the black data points don't follow the purple. So we see an excess beyond all the background. And here background means everything that gets created in the Earth's atmosphere. So we see celestial neutrino emission finally in 2013. This is the universe emitting high energy neutrinos. These weren't created in our atmosphere. So that was great. We got a lot of press. It was a lot of fun to talk to these mass media organizations that I read about every day. That was fun. And then our next milestone discovery comes 5 years later. So 2018, it's the, again, we are on the cover of Science, and you can read the cover already, Neutrino from a Blazar. So we had 2 articles, 2 papers in that edition of Science about the first high energy neutrino source that we think we saw. And there's reason why there were 2 papers. So This is kind of the summary of what happened in 2 plots. So here is the light curve measured by Fermi-LAT, which is a space-based gamma ray telescope. It is measuring the flux from a blazar known as TXS 0506 056. And they have many years, 9 years of data here. And then there's all of a sudden this big flare that they hadn't seen back in 9 years. And while they're seeing this flare, we get a very high energy neutrino. It was so high energy that it's exceptional for us, even for us. And that neutrino seems to come from the same location. And so that is the first paper. And this is pretty unlikely. It's so unlikely that this is a 3 sigma effect. So the other thing we did was, now that we knew that this blazar was somehow special in some way, we don't know in what way yet, but we know it's somehow special. We looked at the neutrino light curve, if you will. So this is, again, the years in the x-axis, and you can think of the y-axis in both blue and orange as a way to measure how flary it was in neutrinos, sort of. And we found this fairly large flare between end of 2014 and 2015. So this was a retroactive finding, but this was our second paper in the same science article that we did. So 2013, we know the universe emits high energy neutrinos. 2018, we think we found the first one that we can identify as a high energy neutrino emitter. This generated more press and also a press conference at the National Science Foundation. So we got all dressed up and played scientists, which was fun. Okay, so there's more interesting spots coming. Again, this is 4 years ago, 2018. So now the cycle should be that we should have more fun things in the pipeline. One thing you can read in this 2020 PRL paper is we do a scan of the whole sky, and one of the brightest spots, actually the brightest spot in the sky, seems to coincide with the starburst galaxy NGC 1068. So you can read about this in this paper. This is about 2.9 sigma.
Please wrap up.
Okay. Another one is the galactic plane. So this, I'm partial to this because this is my group, but in 2019 paper, you can read about 2.1% p-value. So more interesting spots are emerging. We're following up on these. We like them. So this is in lieu of a conclusion. I like to show you the Milky Way from the South Pole. This is our galaxy, our galactic plane, and just hammer home the point that what IceCube is doing is looking at the universe in high energies, in neutrinos, from the Earth's South Pole. Thank you.
Thank you very much. We welcome Dr. Ferguson.
Not doctor, just a grad student still.
Okay, so future doctor, share your screen, please. Floor is yours. I will give you 1 minute before the time's up, okay?
Okay, the slides are coming through.
Yes, you can start.
Okay, great. Good morning, everyone, or I guess good afternoon or evening, depending on which time zone you are currently in. I'm Kyle Ferguson. As I said, I'm a PhD candidate at UCLA, and I'm a member of the South Pole Telescope, or SPT collaboration. I'll be talking today about an analysis that we did using SPT data to search for ultralight axion dark matter. So first, just a little bit of science motivation. I know not everybody in astronomy. So when we astronomers look out into the galaxy, we try to take a cosmic inventory, figure out sort of what is out there. And we find something interesting. You know, all of the matter that we interact with on a day-to-day basis that makes us up, that makes up the planet and everything around us, is only about 5% of the total energy density of the universe. About a quarter of it is this dark matter that interacts the same gravitationally as regular matter, but doesn't seem to interact with light, or at least interacts very, very weakly with light. And then most of the rest is this even more mysterious dark energy, which sort of behaves on its own way, but which won't be the focus of this talk. So when we've known about the existence of dark matter for decades at this point. And despite that, and despite the work of many, many people working very hard, we still don't know what it is. There are a number of candidate particles. I'll be focusing on one specific one, which is the axion. So The axion is particularly interesting as a dark matter candidate because it has a motivation that is completely independent of particle physics. So although it serves as a nice dark matter candidate, it also ends up solving, independent of astrophysics. It ends up solving a particle physics problem called the strong CP problem. I won't go into all the details, but basically there's a parameter in particle physics in the strong force that is sort of fine-tuned to 0, and we don't really know why it should be that way. And if you introduce the existence of axions, then that kind of solves everything and makes the math work out all nice. So axions, or more broadly, axion-like particles, they are compelling as dark matter candidates, I think, because they have this external motivation. And as you can see by this parameter space plot here, which plots the coupling constant between axions and photons as a function of axion mass down here on the x-axis. You know, there are a lot of collaborations, a lot of people doing a lot of interesting work trying to find axions. None have done so yet. In this talk, we'll actually focus on ultralight axions, so things over off to the left of this plot, roughly below a mass of about 10 to the minus 18 electron volts. And although there are fewer experiments looking down in this mass range, this is interesting for dark matter because when you have ultralight particles, they have the possibility to resolve some discrepancies between the observed cosmology and the standard model cosmological predictions on small scales, things like the core cusp problem, for example. So how do we look for axions? Most experiments will take advantage of the fact that we expect axions and photons to couple, you know, that coupling constant as I showed on the left side. And specifically in this analysis, what we look for is as a linearly polarized photon is traveling through an axion field, the polarization of that photon will pick up a rotation. So that's sort of drawn out in this cartoon schematic here. Let's imagine that the axion field is completely localized to within this sphere, and the strength of the axion field is given by this dotted sinusoid. As we send in over here on the right, our linearly polarized photon, it's traveling along, and at first it has the same polarization, and once it hits the axion field, we see that it starts to rotate, first one direction then another, and the amount and direction of rotation are given by the strength and sign of the axion field. And then as the photon leaves, it has the same polarization as when it started. So the total amount of polarization rotation is dependent only on the difference in axion field between photon emission and photon absorption. It's kind of like the electrostatic potential in that way, where it's a path-independent effect. It only depends on the initial and final positions. So we want to try to find these things, and this is an astronomy session, so we want to find them with a telescope. What is your best option here? Well, when we're looking at these ultra low masses, the axions behave less like a collection of particles and more like a classical field, as I kind of alluded to on the last slide, or Bose-Einstein constant. And so this axion field will take on an axion field value, and that value will oscillate in time with a frequency that's proportional to the axion mass. So what we want to do is basically try to measure the oscillation of the local axion field around the Earth. So to do that, we have to find a static, polarized, distant astrophysical source. And we want to that to be static so that any polarization oscillation that we see, we know is caused only by the oscillation of the local axion field. As a second consequence of the fact that we're looking at these ultra low masses, that means that the coherent length, excuse me, the coherence length of the axion field will be extremely large, you know, on scales larger than the size of the Earth or even the solar system, these masses. And that means that this oscillation should be in phase across the entire, excuse me, I haven't had my water this morning, that's pretty early where I am. So the oscillation will be in phase across the entire sky. So this means that you can have not only point sources, but even extended astrophysical sources with which to search for this effect. We have such a source in the cosmic microwave background, the CMB. If you're unaware of what this is, it's basically leftover radiation from the Big Bang that we can still observe today. And this is exactly what we want. It's a static polarized astrophysical source. And so what we want to do is measure the polarization of this source as a function of time and look for this oscillatory signal, the axion signal, within that polarization time series. So we do that with the South Pole Telescope, SPT. SPT is a 10-meter telescope located at the Scott Amundsen South Pole Station. It observes the CMB in 3 bands centered at 95, 150, and 220 gigahertz. And the current camera on SPT is SPT 3G, the 3rd generation. This has about 16,000 transition edge sensor TES detectors. And the SPT 3G survey is a fixed patch of the sky about 1,500 square degrees in area, about 3.5% of the sky. And so what SPT does is it observes this patch of the sky multiple times a day, day in, day out, for years on end. And this is what makes it so well suited to do this type of axion measurements. If you're looking for a small time-dependent effect like this, you want to have a fine time resolution, so the multiple observations per day, and you want to have a long time baseline over which you can integrate, which helps get your total noise down and also allows you to be sensitive to the longer timescale oscillations. So we're sensitive to oscillations over many orders of frequency magnitude, which translate to many orders of axion mass magnitude, because again, the axion field is oscillating with a frequency dependent on the axion mass. Additionally, SPT's high angular resolution allows it to take more sensitive instantaneous measurements of the polarization of the CMB, which allows it to set stronger limits on this type of thing than an experiment like Bicep Keck, another CMB experiment at the South Pole, which has a coarser angular resolution and has done a similar analysis. So I know I'm approaching my time, so I'll just really quickly flash some results. This is the time series that we measured. Polarization angles in 95 and 150 gigahertz using 1 year of SPT 3G data, the 2019 observing season. As you can see, there's no oscillatory signal that jumps out by eye. And when you go through all the math, we do find no evidence of an axion-like signal in our data. So what we are able to do is set a limit on the axion-photon coupling constant. The limit with 1 year of SPT 3G data is shown in red here, with a smoothed approximation shown as the black dashed line. And again, we set a stronger limit than Bicep Keck did, even using 4 years of their data, just because we have this high angular resolution. And we are beginning to set limits that are competitive in this region of parameter space with the other limits that exist. And we believe that once we use the full data set of SPT 3G, we can set even stronger limits. And then with future CMB experiments, even more and more stronger limits. So there is significant discovery potential for this type of thing. And that's all I have. So I just want to thank my collaboration and especially my co-lead on this project.
Thank you very much. Any questions, please write it down in the Q&A facility. And now we welcome Dr. Albrecht. Please, Dr. Albrecht.
Yes, hello, and
please share your screen. And we invite all people of all these collaborations to get in touch with astronomy and astrophysics in Antarctica and participate and continue participating in the SCAR Open Science meetings. You can share your screen. There's a green button.
I understand. I have an unusual problem. I think I have to switch the computer. Can we switch briefly? Somebody else can go next, and I'll come.
Okay. So we welcome Amy Connolly, Dr. Connolly. Thank you. The floor is yours.
Sorry, I hadn't muted. Okay, let me try again. Unmuted.
All right, thanks for allowing me to speak about the Ascarian radio array. I'm speaking on behalf of the collaboration. So the field of multi-messenger astrophysics is a rapidly expanding field that now includes 4 messengers that allow us to probe high energy astrophysics with the newly discovered gravitational waves and astrophysical neutrinos. As Albrecht will talk about next, IceCube has observed the astrophysical neutrino flux, and we heard about this before as well, up to about 10 to the 16 electron volts. That's about 1/1000th of a joule in one fundamental particle. But we expect neutrinos to go to much higher energies than this. But the optical technique that's been so successful up to these energies starts to become unfeasible at much higher energies because of how densely it needs to be instrumented. And so at the highest energies, it looks like strategies that use radio techniques are the most promising. The reason why there are such strong motivations for expecting neutrinos at the highest energies is because we have observed charged cosmic ray particles up to energies above about 10 to the 20, and candidates for what could produce could be producing those cosmic rays include things like active galactic nuclei, which are black holes accreting mass, and gamma ray bursts, which are believed to be from star collapse and mergers of neutron stars. And whatever sources are producing cosmic rays up to these highest energies are also expected to produce neutrinos. And then also the cosmic rays themselves are also expected to produce neutrinos en route after they've left the sources. And the Ascarian radio array is one experiment that takes the approach of searching neutrinos using a radio technique. So ARA consists of 5 stations of antennas deployed up to 200 meters depth in the ice. And we search for the radio emission that would be produced by a particle cascade induced by a neutrino interaction in the ice. This emission is called Ascarian emission, and it gets emitted at about 57 degrees, which is a Trinkoff angle in ice. On the right-hand side, you can see, so we heard about how large IceCube is, but on this picture, it's just that blue region there. You can see the 5 ARA stations as the red diamonds here. And the orange region here is a proposed expansion of the optical component, and the purple crosses are a proposed radio detector that would be part of the IceCube next generation array. So ARA is an international collaboration composed of these institutions. You can see the picture in the upper left of the ARA deployment team that went out to drill. This was during the drilling of one of the stations of ARA. So ARA consists of 2 types of antennas. One type is designed to detect signals that are vertically polarized, and that is a so-called birdcage type antenna that's in the center here. And we also have antennas that are designed to measure horizontal polarization, which can be challenging when you're deploying antennas down a vertical hole. And on the lower right, you can see a view when you're looking down on one of the holes during deployment. And on the left, you can see a close-up of how the ARA stations are arranged relative to IceCube. Okay, so the first ARA prototype deployment happened in 2011. What have we learned so far? So we learned that we can operate the detector at the pole year-round. And if we integrate the number of stations times the number of years over that time, we've accumulated about 25 station years of data. We've performed sensitive searches for neutrinos in the noise environment near South Pole. And we have the best constraint on the neutrino flux from any in-ice radio detectors using only a subset of our data. In the upper right is a figure from one of those searches, and the 2 main parameters that we use on the horizontal axis is the strength of the signal, and on the vertical axis is a measure of how consistent that signal is with a plane wave solution when you look at the timing of the signals as they arrive in the antennas. A signal would be in the upper right here, and seeing no excess above background that allows us to set a constraint. We've performed targeted searches for neutrinos from astrophysical sources, and we even made a serendipitous measurement of radio emission from the sun during a solar flare in 2011, which allowed us to validate our pointing on the sky. We've improved our sensitivity to weak signals with a trigger that uses a phased array approach. And then we followed that with an analysis that was more sensitive than we could have been if we had only used the previous design of the trigger. And importantly, we have deepened our understanding of the South Pole ice properties. This is crucial for interpreting our results and for identifying new signatures for how we can identify neutrinos in favor of backgrounds. So one such signature is the expectation that a neutrino that produces that is at a neutrino interaction from deep in the ice would produce this double pulse signature. So we have this direct solution shown here in blue, and then this refracted solution where it goes up and comes back down. And this comes about due to the fact that the index of refraction is depth dependent in the region called the Föhn in the top 150 meters or so in the ice. And we see this double pulse signature. This is important because it's a signature that helps us discriminate from backgrounds, but also that time difference helps us to reconstruct the distance to the interaction, which is important for reconstructing the energy of the shower. We have this really important data set from the SPICE pulsing campaign. SPICE was a core that was drilled to about 1,750 meters, and the core was removed and analyzed by glaciologists. But we used the hole to deploy a pulsar that was lower down into the hole, and the pulses were received by the 5 ARA stations and also the Adriana station that was at the surface. This has been really important for calibrating the detectors and for understanding ice properties. One thing that we saw that was unexpected was variations in the polarization that we had trouble explaining at first. So the plot on lower right shows that in one of our stations, we observed an oscillatory behavior in the polarization as the pulsar was lowered. We also saw that in station A1, we actually saw more signal in the horizontal polarization than in the V-pole polarization, even though the pulsar was transmitting in V-pole. And I offer an explanation in this in the lower right, which is that at radio frequencies, the ice, as you heard, is birefringent, but at radio frequency that acts like it's biaxial birefringent, which means that the eigenstates for the polarization solutions rotate in non-intuitive ways as it moves through the ice. So still ahead for R, we have really important developments coming. So the team is working on a search from the full 5-station data set. We'll be looking at uncharted parameter space, which means that a discovery is possible. So look for those results in 2023. We'll follow that with targeted searches for neutrinos from astrophysical sources, and those will be strengthened by the next bullet, which is that we're quantifying resolution on measurements of the signal properties essential for neutrino characterization. So this includes polarization, which is important for neutrino direction, and distance, which is important for neutrino energy. That's coming very soon. And we're developing the tools to search for ice cube R coincidences, which would be rare at the order of about 1 to 2% of events that R would see, but they would be richly informative. We will continue with precise calibration of ice properties using existing pulsar data, existing radar data, and any further pulsar data that we can take. And we will continue to serve as a crucial role as a test bed for a next generation array. On the right shows the landscape. Sorry?
1 minute,
1 minute?
please wrap up.
Okay, perfect, thanks. Okay, so on the right shows a plot of the landscape of where ultra-energy neutrino astronomy is. On the vertical axis is the neutrino flux. On the horizontal axis is the neutrino energy. You can see on the bottom, these curves show kind of a range of the predictions for where the neutrino flux would be from the cosmic rays producing neutrinos en route. And on the left side, you can see the measured ice cube flux coming in there. As you move from the top right of the plot down, you can see the solid lines are the measured constraints on the flux that have been established so far. And the dashed black line here shows ARA's reach based on our data set that we'll have in 2023, just next year, at the trigger level, and that's a single event sensitivity. So that's how far we'll be reaching down. So we're very excited to be probing this new parameter space. ARA is the most sensitive neutrino detector above about 10 to the 17 and a 5, above about 10 to the 17 and a half eV with the data set we have. We're accumulating a world-class data set. We have exciting science results to come. And ARA, with its proximity to IceCube especially, continues to serve as an ideal test bed for next generation South Pole Array. Thanks to NSF and ASC for their support for ARA operations. Thank you.
Thank you. Now we welcome Dr. Albrecht, if now it's available.
Yes, okay, I'll try this again on a different computer. And okay, can you hear me?
The floor is yours.
Okay, thank you. So I'm going to talk about IceCube future upgrades. Albrecht Carli, University of Wisconsin-Madison, speaking for IceCube, for the IceCube Gen 2 collaboration. This is a picture at the South Pole, in the South Pole winter, by one of our winter rovers on the way to the IceCube laboratory, the only building structure that is above ground. Everything else is below. So you have heard about IceCube, and on the right side you see a picture of an energetic neutrino event that has been discussed, and I'll show this picture to pause here for a second. And with the IceCube Gen 2, with the higher energy, with the expansion that I'm going to talk about, one thing we can do, we realize that for high energy events, we need actually a little bit fewer sensors, and we can increase the spacing and still analyze such an event as shown on the right quite well. So if we want to learn much more, build on IceCube discoveries and learn more about the high energy universe in new ways, we do require a new instrument. IceCube was in operation now since in full completed in operation since 11 years. And we have a terrific amount of statistics, but we want to learn more about the origin of high energy, of cosmic neutrinos, cosmic rays, extreme environments in the universe, the nature of neutrinos, and the nature of dark matter. So here is a quick upshot again on the landscape of multi-messenger astrophysics. You see here in the neutrino sky on the left, and on the right the spectrum is multiplied with E squared, the gamma ray observed gamma ray flux. You see, watch the energy scale. It goes from 10 GeV to 10 to the 11 GeV, so it's an enormous scale. You have the gamma ray background, the neutrino background, and the cosmic rays flux. And we have the neutrino flux did not exist before, and we have now data. We want to learn more at low energies using oscillations, and especially at high energies. This plot ranges out at about 5 PeV or 10, and we want to have more resolution, more than these data points that we have here, and we want to extend to higher energies. We're doing it in two phases. Phase one is the next step. It's the IceCube upgrade. That's an ongoing project, and it's scheduled for completion in 25-26. The objective of that upgrade is it's a moderate scale upgrade compared to IceCube, is to improve the science capabilities of IceCube at low energies, to improve the capabilities of IceCube at high energies by improving our understanding of the ice that we have heard talk just a bit earlier, and to do technology development for the upgrades beyond IceCube, beyond this one, for the next stage. What it consists of are 7 strings. They are the red dots here. On the right, we see the IceCube footprint. And in the very center, there is a dense core. It's small compared to IceCube, but it's still 5 or 10 megatons of target volume.
and it's very densely instrumented. And that allows to lower the threshold, the energy threshold. Here's an event, a simulated event for in the ice cube, in the center of ice cube now, which includes some additional strings already. And on the right side, we see the same event simulated in the ice cube upgrade. The energy is 25 GeV, and that is an ideal spot to do neutrino oscillation physics. One thing we want to do is, for example, how do electron, muon, and tau neutrinos, specifically muon and tau neutrinos, relate to each other and transform into each other. Here's an example of the performance of the ice cube upgrade after only 3 years of operation in a simulation. So what we see here is a sensitivity measure of parameters that determine the relation of muon and tau neutrinos and how they oscillate into each other. Muon neutrinos may propagate from the other side of the Earth, and as they propagate through the Earth, they may transform into tau neutrinos. Thus, they disappear as muon neutrinos and appear as a tau. When we do a full analysis, then we don't need to analyze the entire, what this plot exactly means, but you see a lot of curves, contour curves. These are error contours from major experiments that exist today. And what you notice that the red curve is smaller than all the others, and it will be an excellent instrument to analyze these neutrino properties in a very short time. We also want to learn more about ice. So there are many special instruments, calibration instruments on that, on the ice cube upgrade, on those 7 strings in the center that will allow us to do more precise measurements that Dima Chirkin just talked a little bit about earlier. And that will allow us to learn to improve the entire ice cube by recalibrating, and we can then even reanalyze past data. Then the phase 2 is a bigger expansion, or in the scale and spirit of the high energy ice cube array. It consists of 3 components. The main component is visualized here on the right. So one is an optical array that is substantially larger, 8 cubic kilometers, so 8 times larger than ice cube now. An air shower array on the top, and a large, quite substantial radio array for detecting higher energy cosmic neutrinos. So if you look at the right here, we see the ice cube array with 1,000 meter extension. And then the Gen 2 array extending to 3 kilometers. It also extends vertically, it goes a little deeper and a little shallower, because we now learned that we can do that the ice is suitable to also extend the vertical range. Here's the landscape of ice cube Gen 2, for the full program, and how these detector components relate to each other. I start here with ice cube, the third from the left. That's the ice cube array. When that starts, has an energy threshold of about a little bit below a TeV. It has this, we are doing this infill on the right that will improve at low energies. Then Gen 2 will have a threshold of about 5 TeV. So we are pushing a little bit up the threshold, but we are gaining an enormous amount of volume compared to ice cube. And then we go one step further to the left, and there's the Gen 2 radio array, where we would have radio antennas, just like the ARA array would be a good, it's the ideal reference, and happens to be at the South Pole, that we would extend to almost 20 kilometers away from the South Pole station for a widespread radio array to view about 1,000 cubic kilometers of ice, to have sufficient target for the rare flux events at the higher energies. So how is it possible that we can increase the volume by so much? One is the ice is very clear, even better than what we thought it was in ice cube, so it's very transparent. The science goals have shifted a little bit to higher energies based on the knowledge gained with ice cube. And we have a substantially improved sensor design. So here are pictures of sensors. On the left side, that's the ice cube optical sensor. It houses a 10-inch photomultiplier. In the middle, we have 2 types of modules that will be deployed in the ice cube upgrade. One is, you see there's a multi-sensor module that can look in all directions. The other one is sort of kind of narrow, and because narrow is good in some sense. Yep. And the right is for Gen 2 is sort of the compromise of both components. Here is a picture of the radio detection. This is exactly the detector that is planned. This follows quite the ARA spirit and will have 300 stations of order viewing 1,000 cubic kilometers of ice in this array, as shown here on the left. And it allows a substantial increase in sensitivity by about 2 orders of magnitude above 10 to the 17 electron volts. And here is a summary of the sensitivity that we can achieve with IceCube. A factor of 5 improvement of the sensitivity for point sources at lower energies, and yet about 2 orders of magnitude improvement on the right at higher energies. You see here IceCube sensitivity, and here IceCube Gen 2, and compared to optical Cherenkov telescope sensitivities. So the takeaways are that the IceCube upgrade, 7 strings, that project is underway and will be deployed in 25-26. With Gen 2, we want to increase the size of IceCube by an order of magnitude. We received very good recommendations from Astro 2020 decadal review. Conceptual design exists, and we are improving a lot of technology, and a technical design document is in preparation for release later this year. Thank you.
Thank you, Albrecht. Well, now I will have just 8 minutes to give my talk. So I will pass some of the slides. I will talk about the Argentine Space Weather Laboratory activities in Antarctica with all these co-authors. We have, this is our website. We are an interinstitutional group. These are the institutions for space weather instrumentation, development, research to operation, and operation to research, real-time monitoring of space weather conditions. We participated in the recent international whole heliosphere and planetary interaction campaign during January to February 2020, accompanying NASA's satellite Packer Solar Probe. We are full member of ICES, that's International Space Environment Service, and we were officially appointed as the Argentine Regional Warning Center. We participated in the recent implementation of the Space Weather Information Service to the International Civil Aviation Organization for decision making. And this is to illustrate that we are the ground-based support, making our data available to the Parking Solar Probe. We have also an operative website. We have a warning by email service. And we also provide products on solar activity, interplanetary medium, radiation belts, magnetic field, ionosphere, and cosmic rays. We study astroparticles as tracers of space weather in an interdisciplinary approach. We study the solar wind and the magnetospheric modulation of the galactic cosmic rays, the secondary cascades of atmospheric radiation at ground and flight level, of obviously the connections with the atmospheric physics. We also study the decreasing in cosmic ray fluxes due to ICMEs or other structures that we call Furbish events, and also ground level enhancements of the radiation fluxes. We study the transport of the cosmic rays in the heliosphere, the magnetic reconnection in the magnetosphere, and of course the Sun-Earth human life connections, especially for astronauts in space of transpolar flights. In the summer campaign of January and March 2019, we installed our laboratory in the Marambio station. And among the instrumentation, there was a water Cherenkov detector of the Latin American Giant Observatory collaboration. The science we can do, you can see that as long as the CME or ICMEs, that are the coronal mass ejections or interplanetary coronal mass ejections or magnetic clouds, depending on the flux probe structure. They prevent the diffusion of cosmic rays within the structure, which is translated into a decrease in the cosmic rays observed on Earth. And depending on the relative position of the Earth respect to the flux probe, there are several different shapes of the decreasing of the flux, as you can see from this figure from Richardson and Kane, 2011. And as long the flux probe is expanding from the sun to the Earth, there's cross diffusion of cosmic rays into this structure. Here you can see the recovery phase of the Forbush decrease at the beginning of September 2017, measured at Buenos Aires, and the comparison with the Pierre-Auger scalars for the same period of time. In the summer campaign, the last summer campaign, we implemented a faster acquisition system, providing full compatibility with the other Latin American giant observatory nodes. Also, we established a new automatic thermalization system to prevent thermal drift of the electronics. 2 additional acquisition modes are being tested with different thresholds, and an inexpensive magnetometer design is being tested to space weather purposes. This is to illustrate what I have just said. We have a quasi-real-time available data from the Antarctic lab to the Buenos Aires servers. We were operating through the whole COVID situation. This is to illustrate how well the thermal control system is operating. Here you can see the instrumentation, additional instrumentation that we have. In green, you can see the permanent basis, and in this is more of orange, you can see just the summer stations. In the Marambio, San Martin, and Belgrano 2 stations, there are magnetometers, ionospheric sanders. This is under repairment right now, and ryometers. This is instrumentation of San Martin station as well. The magnetic disturbance of August 25 in 2018, as were studied by us at the flux magnetometer in San Martin station, you can see the disturbance. And as it was seen by Belgrano 2 stations, this is, remember, San Martin is here and Belgrano 2 is here. And I'm very pleased to show you this because this is our first Forbush decrease measured at the lab in Antarctica. It was a coronal mass ejection heading towards Earth and arrived on October 11th of 2021. The origin was an active region, 2882, that produced an M1.6 solar flare. And you can see this is also in one of the products we offer, and you can see the website direction for the cosmic ray flux in almost real time, 5 minutes. And this is the Enlil simulation for the arrival of this CME. So I have just up with my time. So stay tuned. We are studying events, getting statistics and validation of our data. This is our website and our product website. Thank you very much. So I urge you to also look at the poster sessions that we have, and we appreciate all your contributions. We have just 1 minute to wrap up, and if someone has any question, please use the Q&A facility. Thank you.
Thank you, Adriana. I think we are out of time, and
yes, indeed,
everybody's quite exhausted after this marathon of so many talks so quickly. I think it was really great to catch up with everybody and see what everybody's up to. Some amazing things coming up under the horizon over the next few years at many sites. So I want to thank everybody for participating, and I hope you guys get to enjoy more of the SCAR meeting. Some of you may also be following what's happening at the IAU at the moment as well. So, you know, multiple conferences on all fronts. Good luck with all of that. So I'm going to say good night in my particular case. It's exactly midnight. See you all. And I'm going to stop the recording right now.
see you. Thank you.